So thanks everybody for coming to this second day of Jump Dev. So this is actually a Julia and Jump focused conference, but we have a tradition of inviting speakers from alternative modeling languages to come and tell us about their work. And this year we've invited Ross from Google to come and talk to us about some new work they've been doing in Google OR tools. So Ross, take it away.
Okay. Hi. Thanks. So I'm Ross. Thanks for the invitation. So I work for Google and Google Research, and I'm on the operations research team, and we have an open source modeling, an open source library that includes mathematical modeling as part of what it does. It also has solvers. It's called OR Tools. And today I'm going to talk about MathOpt, which is kind of the V2 version of mathematical modeling for OR Tools. Okay, so what is MathOpt? So it's a library for solver-independent optimization modeling, and I guess for this community, I guess I don't need to sell the idea that you might want to do solver-independent modeling. That's what Jump does. And so you can access it from Python, Java, and C++, and there will be more languages to come. And it supports, we try and support like a wide range of features that solvers have: incrementalism, callbacks, duality, and some simple conic and nonlinear constraints. And we don't have 43 solvers, but we have a reasonable number of solvers, at least for people who are interested in solving MIP problems. You can use Gurobi, and you can use Skip and Heis. So these are like, if you're license constrained or not, there'll be something here that does something good for you. And it can solve. This is kind of one of the interesting features of MathOpt. It's designed from the beginning to either solve locally, to solve in a subprocess, or to solve remotely on another machine. And when we say solve, like our goal is to support all of the features, including incremental solves and callbacks, when the solver is in a separate process from the modeling code. And so we use it in production at Google, and it's distributed as part of Google's open source OR tools. Okay, so a very simple example of just what the code looks like if you're a user. So let's say we had this very simple pip, maximize x plus 3y subject to x plus y is MLS 1.5 with an integer and a continuous variable. So first you would build the model, and because this is Python, we can kind of make the code look like the math. That's the goal. So we make a model, we add two variables, and then we can use the operator overloads in Python to build linear expressions to set up the objective and constraints. Then we set the parameters, and MathOpt, so we take it a little further than Jump in terms of these trying to have solver-independent parameters. It's a hard problem because the solvers are all different. But I mean, Jump definitely has enabled controlling the logging is one of them. And then we call solve. And this is like just a one-shot solve. There's separate APIs for the one-shot and incremental solves. And so you set your solver to Gurobi, you get the result out. And here we're just checking that it was optimal and printing the results. So very kind of simple code for a simple use. So who are the contributors? So this is a bunch of people have worked on this. I'm going to try and say everything that's correct. I may make some mistakes because it's just a lot of code. So you can see here the top. There are three core Jump members in bold here: Miles, Joey, and JP. So a lot of the work that we've done is we took a lot of inspiration from Jump in designing this. And you may be wondering, JP, he's the manager. How does he have time to write so much code? And how you do it is you make a new project inside of MathOpt. You write 20,000 lines of code. Then you fork a file into 5 files, and you 5x your contribution. And then you move all that code out to a new directory and count it again. So that's how you get to the top. That's why JP's in charge. So anyway, so an outline for today's talk. Why MathOpt? And what is special about doing mathematical optimization at Google? How is it different from what you see outside? And then a little bit about how MathOpt is built. And I'll show some benchmarks and future work. Okay, so what are some applications at Google of optimization? This is not loading well. There's supposed to be some videos here, but oh, there we go. See if the internet is gonna. Well, okay, we may not get to see it all, but these are YouTube videos that just may not be on the internet or the internet connection's not working. Okay, so there are many applications at Google of optimization. Like you can see the bottom right corner, there are over, if you just look through the code, you'll find over 100 people who are solving MIPS at Google. Google has one mono repo, so you can look through the code. And the most common application is probably this kind of process machine assignment where you have tasks, you have machines, you need to figure out which machines are going to run which tasks. Very, very common problem at Google. Another big problem is in the supply chain setting where they're buying parts for the data centers and then shipping these parts around. But I mean, Google works on a lot of different things. There are network design problems, chip design problems. This robotics problem down here, this was actually done with a CP solver by the Google X spinoff Intrinsic. And these robots were being controlled by, like a CP solver was doing the plan of what order to move all the different arms in. Yeah, so many different applications. The one I wanted to show you that was a YouTube video. This is work from 2011 where they had a video that was shaky and then they solved an LP to make the video look not shaky. And that's interesting because it can run on the device or it can run on the server. So just another thing Google needs to be able to do. Sorry, the video is not working. Okay, so why is Google different? Okay, so we have great food, but I guess this was the wrong question. Why is optimization at Google different? So I'll give maybe 3 reasons. And like this is kind of motivation for why we built MathOpt. So the first thing is from a reliability. Like for many of our applications, it's very important that the code will never crash. In particular, we don't ever want a segfault for like if you've worked in C++. And we need to, like the users want us to give them a strong contract, and the users, if we break the contract, then the user's code crashes. So this like, we have to both have a contract and not break it. So this kind of goes into this reliability never crash. And why is this a problem for us? Well, the biggest issue is that a lot of our problems, I mean, we do solve strategic problems, and we also solve operational problems where you'll have a system that's solving 100 MIPS every minute. And it's fully automated, so no one can babysit this. No one can babysit these solves. So it just has to be very reliable. And yeah, and as I said, if you have a weak contract or you break your contract, either way, it's going to result in a crash in the user code, or it'll slow down developer time, make it hard to write code. And we'll talk about how do we address reliability kind of coming up. So second, solve hard problems. And this is actually less specific to Google. Everyone has hard problems. Everyone has large optimization problems. Maybe something that is a little Google specific is this, like we do have some near real-time stuff where we have 10-second, 30-second time limits on problems that are pretty big because we're using it operationally, not strategically. And Google has this joke, I can't count so low. Like when you tell someone that like you can only solve things on like 100,000 variables, they're very surprised. They're like, that's a tiny number. What are you guys doing? I don't understand your field. So. Okay, so last, from a maintainability perspective, and what do I mean by maintainable? What I mean is that we can safely make changes and be confident that we're not going to break something. And why? Because we can't crash. And why are there so many changes? So like our code has dependencies inside of Google, and our dependencies are changing all the time, so we have to change as well. Users request new features, the solvers need upgrades, and like there's no branch. Everyone's building from head, so you have to be green. Everything has to work at every CL. So it's in this setting like you need to know that everything is safe when you make a change. Okay, so maybe these are the 3 things that we want to accomplish with MathOpt. And hopefully, now I'll tell you what MathOpt is, and maybe at the end I'll convince you that we did it. Okay, so maybe first I'll just give kind of a very high level, like what is the path from the user trying to solve a model to it actually getting to Gurobi. So hopefully this graphic isn't confusing. I've never tested it before. You guys are the first users of it. So what does the experience look like? So the user is writing Python code. They specify their model. So they make a model. They add a variable. They maximize that variable. Simplest model. And like they're kind of interacting with the client library, which is returning stuff. Those arrows are kind of omitted from this picture. Then they make a solver object where they pass in the model. And what happens here? So under the hood, now we need to cross the language boundary to make the solver object. And the model is converted into this highlighted model proto, and this is using protocol buffers, which is it's kind of like JSON, but it's a structured format for encoding data. And it's a binary format. So we send the model down to the MATLAB core. Now we're in C++, and the MATLAB core will then go to Gurobi and say, Gurobi, please make this model, add the variables, update the model. Then the user calls solve. So they set their enable output to true, and they call solve, passing the parameters down. Again, we need to cross the language barrier. We send the parameters down as a protocol buffer. And inside the core, we then tell Gurobi to set the enable output true and to call optimize, and we get the result back. We extract the result from Gurobi, and we build a new protocol buffer, which we then send back to the client library, which then sends the result back to the user. So this is kind of the flow. And in different languages, you'll have a different implementation of the client library, but it's going to do the same thing. It's going to send protocol buffers back and forth. Yeah?
Question, why are you using protocol buffers here? Is it because it's running on a different Docker container or a different machine?
Yeah, so this is a good question. So we want the flexibility to run the core in a different process or in a sub-process or on a different machine entirely for remote solve. But even for local solve, there are some advantages to having this strong separation between the client and the server. And then the question is, like, can we afford it? How much does it cost us to go through this extra layer? And we'll return to that at the end of the talk. OK, so the kind of big pieces are the client, the binary protocol, and the core. And so why did we split up the code this way? And I think Jump has converged on, I'm not an expert on the Jump code base, but I know that you have Jump and you have MOI. So I think you have something similar going on. So separation of concerns, this is like the biggest thing. The client is actually more code than the core. And we don't want to think about the complexity of the client when we're working in the core and vice versa. And like by isolating everything, but going through a pure data format, it just makes it a lot simpler to reason about the code. And also from a modularity perspective, if you don't like your client, you can write a new client in C++ or Python and just reuse the core. So inter-process communication, as I mentioned, like this kind of gives us inter-process communication for free. Another big advantage, and this is something that you guys have in your caching optimizer in Jump, is that we can do, when you interact with the solvers for efficiency, they want to work in batch operations, but the user never wants batch operations. They just want to set and get one at a time, because it's a lot simpler. And we're set up to do that in this setting. And last, when something goes wrong, we can just replay the sequence of protocol buffers to reproduce the crash. OK, so I guess I tricked you guys. The talk just got twice as long. So I'll talk a little bit about each of these three pieces, and then we can kind of return to the main bullets. So what do these protocol buffers look like? So here's like kind of a stylized subset of the model proto that we have. And so there's a message for the variables, a message for the objective, and then the message for the model contains the variables and the objective. And within the variables, there are IDs, lower bounds, upper bounds, and integrality. And so why are there IDs? So we support incrementalism, and when you delete something, when you delete a variable, we don't shift everything down. The IDs are stable. There are pros and cons to doing this. It's just the choice we made. It's a little bit simpler for the user this way. So it's a structured data format for encoding your model. And it's widely used inside and outside of Google in the software engineering world. And there are lots of alternatives to protocol buffers, but this is kind of just the one that is most widely used in Google and has support in many different languages. And so what's nice about this is that you have this, you write down this proto file, and then it generates code in Java, in C++, in Python to help you build these messages. And then we can cross the language boundary as bytes. And so you can see here that like we did, the variables proto is organized as a struct of arrays instead of an array of structs. Like array of structs is easier to work with. Struct of arrays is a little bit faster for languages like Python or Java where there's a lot of overhead to calling new. So that's why we did it. I mean, it was a small win. I don't know if it was worth it, but we did do it. So, OK, and then how does incrementality work in the protocol? So you have this idea of an update proto where you say, what about your model has changed? So some variables were deleted. Some variables have their bounds updated, either a lower bound updated, an upper bound updated, or integrality changed. And then you'll have new variables that you've added to the model. And then there'll be more in this model update proto for constraints and objectives. And so our goal was just to build the smallest possible message to encapsulate the update, because we don't want to send the whole model and then diff on the server, because like we don't want to use, I mean, it's more CPU time on the server and more network space. So it's the client's job to build these diffs. And it's a lot of code to build the diffs, but it's more efficient. OK, so when you have a delete, you just send the IDs of what's been deleted. And everything, any constraint using a variable that was deleted, you don't just send that that constraint has been updated, just that's implicitly zeroed out. Yeah. OK, so and kind of the last part about this, these protocol buffers, is that we have a strong and programmatically enforced contract. And this is, what do I mean by this? So in every protocol buffer, there's going to be a comment saying, what are the rules for this protocol buffer? So the IDs need to be sorted and unique and non-negative, and in this sparse double vector proto. And the values cannot contain a nan, and they must be an equal number of values to IDs. So you have these kinds of contracts in the messages. And then in our solve function, when we call solve, we check. We have a function that will check that the contract is met and return a status error if the contract is violated. And then we can propagate this error in the, so like in C++, in C++ we don't throw exceptions to Google. We have to return an error instead. And then in Java and Python, this will be propagated as an exception. And we check the input to the input model, and we check the output solve result to make sure that everything is OK. And so this is good because it means that we can actually have a contract. If you guys have worked with the solvers, like you'll see they have a giant API, and there's no guarantees as to when any field is going to be populated. You just have to check to see if it's there. So this is something that we're trying to be more precise on. So why do we do this? If you provide a strong contract, user code is a lot simpler. Don't need to have a bunch of conditionals. It makes you end up testing a lot more when you have your unit tests, and you have a powerful combination with a fuzzer. And so this idea of a fuzzer is that you generate random protocol buffers, send them down to the solver, and see what crashes the solver. And this validator catches a lot of issues. OK, so got to speed up, using a lot of time. OK, so next, I'm going to talk about the client library. So what are the responsibilities of the client library? You need to be able to add, delete, get, or set in O of one time for any property of the model. And you need to be able to access the rows and columns efficiently. That's our goal. We need to be able to build these protocol buffers for the model and the model update. And we need to be able to generate our constraints with operator overloads. So if we want to get or set our coefficients efficiently, what is the key task? We need to work with a sparse matrix. We need some way of dealing with this. And it's because our IDs are sparse after deleting variables. Like we are kind of three-way sparse. We're sparse in the rows, we're sparse in the columns, and we're sparse in the non-zeros of the matrix. And then you kind of have all these basic operations of set and get. And the ones that are kind of tricky are get all the rows, get all the columns, and delete a row or delete a column. So the simplest solution you have that gets an asymptotically optimal performance is that you just hash everything. So you have a map from the rows to from the row ID into the column double values. And then you map the other direction from the column ID into the set of rows that have non-zero value. And then so this is a lot of hashing, right? But like you can get an optimal result here. And then when you delete, you just have to, when you want to delete a column, it's a little tricky, but it's relatively simple code. I'm actually going to skip this for time. And we can do better in terms of like reducing the total amount of hashing our code uses with more complicated data structures. And in C++ we do it, in other languages we don't. OK, so I'm just going to skip this how do we build model update protos, because the slide is kind of long and we're out of time. On variables and expressions, so the last responsibility of the client library is to like, so users don't want to interact with ints, they want a type-safe API. So when you say model to add a variable, you get back a variable object, not an integer, and you can set the lower bound directly on that object. And then we have to overload the arithmetic operators to add constraints. And then there's a question of, when you have linear expressions, how do you want to represent them? So in C++, our linear expressions are just a hash map from variable to double, and then the double offset. In Python, we do something a little more complicated, where when you call multiplication or plus, it actually is building an immutable abstract syntax tree, and then you have to flatten it before you can read it. And why do we do this? We'll see on the next slide. And last, we try and leverage the compiler to make it so that way, like, you say add linear constraint and you add a quadratic constraint, it's an error. You're stopped at compile time. OK, so maybe some gotchas. These were kind of fun things about linear expressions. So first, OK, so I have two variables, and I say variable x equal variable y. So is z a Boolean that indicates if they're the same, or is z a linear constraint? So do you have to decide? You don't have to decide. You can have both. And the idea is that you have an object that's both implicitly convertible to a Boolean and to a constraint, and that you can do this in Python and in C++. I don't know how does Julia deal with the situation?
We don't.
You don't.
We use macros.
OK. That's a good answer. Like, was it wise to do this? I don't know, but we did it. So, OK, another kind of gotcha here. So if you call the sum function on the Python's built-in sum function on a list of variables, what is the running time? Is it linear or quadratic? And the same issue occurs in accumulate. And the reason why it can be quadratic, depending on your implementation, is that the sum function uses the plus operator, like the x plus y operator, not the plus equal operator. And so you can end up doing, if the plus operator returns something that is equal to the full output, then you end up doing a linear amount of work for each plus. So that's why we do this deferred evaluation in Python. And just some random stuff that has burned us in the past. So this is on the predecessor to mathopt in C++. The following code compiles, but it does not do what you want. So here I made a variable. The variable is a pointer. That's the type of variables. This is how we represent variables in mathopt. And I add 8 to the pointer, and then convert it to a linear expression. And I am not getting x plus 8. I'm getting pointer arithmetic into garbage memory and bad time. So this is something that we avoided in mathopt by just not using pointer types to represent values. OK, so I think that we're just going to skip this next section. So this is like kind of on the solver side. It's probably the least interesting of the sections. So we'll skip it and go straight to the benchmark. OK, so here's a very simple benchmark I did on the traveling salesman problem. So the goal here was to measure what is the overhead of mathopt in a callback. So the setup, I took 100 cities on IID in the plane, and the distance metric is Euclidean. And we use this kind of standard cut set bit formulation. It's an exponentially large formulation where you need to separate over the constraints as you solve. And I use a callback to add the constraints at every fractional solution. But I don't do exact separation. I do heuristic separation where the time to separate is like linear in the size of the number of non-zeros. So this is, I mean, the details aren't super important, but it's very basic TSP stuff. And then I solve with Gurobi in one thread. And so we'll look at 3 settings. So just Gurobi. So here this is measuring. So this is actually, it's milliseconds, not seconds. The axis is wrong. Sorry about that. So if the time that was spent inside of Gurobi was about 500 milliseconds, and the time that was spent inside of MathOpt was like, I think it was 590 milliseconds. And then kind of this third bar here is what if MathOpt's in a subprocess? How much time did it take? And now it took over a second. So how much of this time was because of subprocess startup overhead? How much of it was because of communication with the subprocess? You can't answer that from this plot. I apologize, and further experiments are required. I guess you'll have to wait for a paper if you want to know the answer to that question. But I believe that the main driver here is actually the subprocess startup is probably about half a second. So, okay, and last demo. So I'm not on the internet. Okay, well, I guess we'll have to skip that demo. I was going to show a demo of the C++ code running in the browser to solve a MIP. And this is done using WASM. So like the point is that the C++ code is portable. It can run on Android, it can run on iOS, it can run in the browser. Okay, so future directions, more languages. We need to catch up in Java, Python. We want to get Go and JavaScript. And we also want a C API, which so that way any language could wrap our solver. And if Jump wants to call glop or PDLP or CPSAT, this could be one path. They could also directly connect to these libraries, but the nice thing about using MathOpt is that the API is very small. There's only 3 methods that we need to wrap in the C API. So we want to add more constraints. We want to add more solvers. So another thing is we need to catch up in open source. Right now, only the C++ stuff works in open source. So we need to fix our build system. All our documentation is internal, and we need to get our RPC mechanism that we use is an internal only one. So we have to switch to. We need to get a version working with gRPC if people want to use the RPC stuff outside. And JP, I don't know if you see JP's talk later, he may be talking about how do we do a better job on making it easy to write decompositions. Okay, so to kind of wrap up, MathOpt is Google's solver-independent modeling library. And so what were our 3 goals? Reliability. So how do we achieve this? Input-output validation, solve in a subprocess, and write your clients without any C++ on the client. This is the best way to not have a seg fault in your code. Powerful. So we had a bunch of, we try to support a wide range of features that make it possible to solve really big problems, and maintainable. So separation of concerns. This is all basic software engineering stuff. Encapsulation, testing, that's the goal. And it's built for Google, but free for you if you use OR tools. And as I said, the open source stuff is lagging, so hopefully it will catch up over the next few months. Okay, thanks.
So we have time for a question from Miles. And I might just ask that you restate the question
Yes.
into the mic for the video.
Do you have a workaround?
Okay, so the question was, so in protocol buffers, if you need to serialize a protocol buffer, you have a limit of 2 gigabytes. And even if you don't serialize it, if you have a vector in a protocol buffer, you're limited to 2 to the 31 non-zeros 2 to the 31 elements in the vector. So right now, I would say that for serialization, okay, the answer for both is no. We have something planned, but it's just not, we haven't worked on it. We will work on it when there's a user who says, like, Google is losing money because this doesn't work. So it will happen soon.
Thank you. So you said that you solve hard problems, many very large, some in real time. How does MathOpt help with solving large problems?
Yeah, okay, so I think that when you have a problem that's really big, like, okay, so what are your options? Like, I think that you doing some kind of decomposition, or this is one good choice. And I think this is how we try and help to solve with large problems. And if you look at how people solved MIPS at Google prior to MathOpt, like, there was no, like, the support for, like, duality, basis, incrementalism, all the stuff was really poor, and it made it very hard to write a high-quality implementation of any decomposition. And this is the problem that we're trying to fix. And like, this is not a problem from the, like, in Julia, this problem is solved. You guys have jump, that's a good job. But like we can't run Julia in our stack, so.
We'll thank Ross for a very good talk. So we actually have a decision now. So Chris is the next speaker, but he's still stuck in Seattle. So we could either keep talking for the next few minutes to Ross, or Joachim can come and tell us about Kubo problems. So maybe if you had questions for Ross, could I have a show of hands? And if there's lots, we will keep talking. Otherwise, what should we do? Should we just keep the discussion? Yeah. So, question.
So you just now mentioned about some decompositions that you are doing that sort of helping with making those large problems solve faster. Can you say something about that?
Okay, so I think that the canonical reference that we have for like a big problem that we worked with on decomposition with BNB-PEP was so Google has a partnership with Lufthansa where they have to solve this operational problem of they have to you have like there's a disruption in the schedule. You have planes, you have passengers, and you have crew. You have to decide who's going to go where to get back on schedule. And like this is a multi-tiered decomposition that they solve the problem with. There's a lot of column generation involved, and like MathOpt was used to make this a lot faster, especially on the airplane rotation side. So that's maybe one example.
Thanks, Ross.
Yep.
No,
He's just going to use this.
Oh, no, this one is too complicated for 5 minutes.
So up next, we have a last-minute talk to replace Chris, who was stuck in Seattle. Joachim is one of the Jump developers, and he's going to be telling us about the work they've been doing on Kubo problems. So take it away.
Thank you. So this is some sort of a quick update on the last year talk. We had a talk on Kubo last year, so if you want more details, go over there. There's a bunch of talks as well, so let me just go through this really fast because we have like 7 minutes. Perfect. There we go. So Kubo.jl, now we didn't change the name. The previous name was 2Kubo, which was the package for doing reformulations to mathematical programming, regular stuff, to Kubos, which are these quadratic, unconstrained binary optimization problems. But now we created sort of a meta package to encapsulate the whole ecosystem. So first thing is that, well, I have a few co-authors in this work. So Pedro from PSR, Nelson from the State University in Rio, Thiago from PSR, and David Bernal from Purdue and NASA. I will skip this. PSR is a company in Brazil that works with power systems and consulting and software development. And, well, this is the jump to Kubo, the thing that I was talking about. You could see from last year's talk. So you can write a jump model. You can call this 2Kubo thing, and then you can kind of use this Kubo formulations in your Kubo solvers. Okay, so we increased the ecosystem. So since then, we added this Kubo driver things and Kubo tools things. So I will talk really fast about them. And everything is in this new Kubo.jl package. You just import that, you can use. There is a paper online explaining whatever we have done. And the nice thing is that, well, actually the challenge is it's a quadratic objective problem with no constraints and binary variables. It's equivalent to a max quad. So why do we care about that? And the reason is that, well, there are some really interesting solvers, many of them in the side of quantum computing, and the idea is that we want to leverage that. And again, you can start with a mixed integer nonlinear program, you convert that to Kubo, and that's the tool that I was talking about. To do that, you need to do some tricks, And I will skip the tricks, which include converting variables from continuous to binary and things like that. So you have a simple problem like this portfolio allocation problem. You try to pass that to D-Wave. That won't work because it only accepts Kubos. But then you can wrap D-Wave in the 2 Kubo optimizer so that it will perform automatic reformulation. There is this analogy. You're going from jump to a Kubo solver. There is this reformulator. It's like, in some sense, like Julia having LLVM in between some assembly thing. Just like everything in Julia, Kubo is really flexible, so you can mess around a lot with that. And well, the thing I want to detail a little bit is, well, now you have jump to Kubo, and then you have to attach a solver over there. And how you do that is you use this Kubo driver package, which is something that is very similar to many things that are already in MathOpt interface. So if you're used to MathOpt interface, you might have seen something like caching optimizer, matrix optimizer, many of these in-between packages that help you move from one place to the other. So this Kubo driver thing is something that helps you wrap your Kubo solver. So if you have something that is just a Kubo solver, you don't have to go all the way and do all the implementation of a regular jump wrapper. You just use this thing and it's really easy to implement. Second thing, okay, so this is just an example of wrapping a solver, which is really simple. We have implemented a bunch of interfaces with that. So there's like 8 right now and maybe more in the next months. And then we were like, well, we're solving a bunch of Kubo problems, so maybe we need some extra utilities. And we sent all of them to this Kubo tools thing, in which we have, well, a few things. One of them is a bunch of specialized data structures that can communicate Kubo models to a bunch of different data formats. It was interesting because we passed some of these Kubo problems to MQLib. So Ian Dunning from Jump, again showing up, but not in Jump, in this MQLib package. More stuff that we do in this Kubo tools thing is you can analyze the quadratic matrix of your thing. You can analyze the solutions in terms of energy and frequency. If you are into quantum computing, you'll know a little bit of that. We can talk more about that offline, and everything is in this Kubo package, and this is pretty much how things are connected. So you have Kubo solvers, they attach to Kubo drivers, they use Kubo tools format. If you want to send them to Jump, you pass through to Kubo, and then you arrive at Jump, but you can also do analysis and handle files. This is kind of a summary of a bunch of things that we implemented comparing to other software that do kind of similar stuff. So encoding variables, you can't, well, because you only accept binary variables, you have to do some binary expansions and things like that. So you can do some variations of that. And which constraints do you handle? Nowadays we handle like linear, quadratic, equality quadratic, SOS. And we're working towards representing this kind of SAT or logic formulation things. That would be interesting to be able to write that as macros in Jump. So that's one of the things we want to experiment soon. Finally, there's just a benchmark we did in the paper. Feel free to look at it. There's one with the traveling salesman problem and another one with the number partitioning problem. We're just showing here that we can build the problem much faster than these other Python packages that even use C++ downstream. So, yep, again, Julia is doing things very fast. Finally, this is what we are trying to do. So bridge the OR people to this quantum computing thing. It's like you don't need to know much about the quantum hardware and things like that. You can just write whatever problem you have in Jump, and it will give you the nice things. Finally, current research and next steps. We're trying to model some example power systems problems, and we are going to do some benchmarking on many of these solvers that we implemented. And thank you for listening.
So next up we have Jean-Francois. Oh, here we are. I was looking around and I couldn't see you, and I missed you right at the front. So next up we have Jean-Francois, who's going to tell us about some constraint programming work that he has been doing in Julia. Once it comes up. And so sweet. And so the time at the back is a little slow, so you've got 10 minutes.
Okay, so I'm just starting and I already have some time constraints. So we are already learning something. Okay, so joke aside, I will try to introduce the constraint programming paradigm because it's my kind of to-go example for today's presentation. Okay, so the idea is like we can model problems with a high level of abstraction that is close to natural language. For that, we define a set of variables, usually discrete. We have a set of domain over the variables, and we have a collection of constraints, so predicates over the variables. Optionally, we can have objectives that can be provided. If you want to know a bit more, we had a talk about this kind of things 2 years ago at JuliaCon. Okay, so this slide is for people watching online that can pause and see some example. I will give one for local people. Okay, so this is a Sudoku. Most people should know about it, but the idea, we have a grid, we want to fill it with numbers from 1 to 9, and we have some constraints like each line, each column, and each block need to be to have different values. So if we look at one example using jump, that was prior to 1.x, so it's old code, but anyway. What we can do with constraint programming is expressing something that says, okay, all the variables in my constraints are different. So then it's become very, very short to express Sudoku, which is just basically all different for variables on the rows, all different for variables on the columns, and the same for blocks. Okay. And the motivation for today's presentation is like often, not always, but often, efficient solvers expect more complex methods to provide additional efficiency. And it's difficult when you're not a technical user. So what we did with constraint learning is an interface to different tools that were designed to smooth that trade-off. The first one is compositional networks that we presented 2 years ago. And the recent one is Kubo constraints. So thank you, Joachim, for introducing Kubo just before. In both cases, we try to learn automatically smarter things just from predicates. So the application of constraint learning are not only for constraint programming, but because that's my specialty, we are currently focused on it. Give a small example based on one of the solver I maintain. So it's a constraint-based local search solver. It's a family of solver or meta-heuristics that model things as a constraint program. And then we kind of use a local search method under the hook. And if we do it in a naive way, like we count the number of constraints that are violated, we have the thing on the left. So we have a lot of plateaus, and our local search method will just go around until maybe, if you have enough luck, you will converge. What we want to do is something a bit smarter. Like on the right, we want to say, okay, this constraint is violated, but by how much? Can you give me something a bit more qualitative? And we can have something like this, where we basically can converge quite fast. And we learn those more qualitative functions from the predicate. So this is just a small experiment. The blue part is actually the naive solver. So, and the three others are like the ICN, so orange and green is our composition network package, and the purple one is the state of the art. So it's like different order of magnitude with the naive one, and we are, well, kind of close to the best thing. Okay, so okay. To go a bit further, why we want to do that? There is a belief, I'm not entirely convinced myself, but I'm still going for it, that most of the constraints in constraint programming can be decomposed into a set of core constraints, which are defined in the XASP3 format. So here is a curated list. And after some analysis, we were able to see that there are only a few types of parameters, like Boolean, dimension, ID, language, operators, pair of variables, and values. Currently, what I present today is working super fast and very efficient for two cases. When we have a parameter as a single numerical value and when we have no parameter. So we still have a lot of work, but still. We went for a second tool. So this one is about learning automatically Kubo matrices from constraint programming predicates. And we hope to actually integrate it with Kubo.jl later on the road. But anyway, so the idea is like Kubo is getting popular, and we can run things on quantum devices or quantum-inspired devices. And what we can do, so we have a set of variables from x1 to x4. We binarize them in a way or another. And we try to look for a pattern, actually combination of pattern that we can recognize. And then for this channel constraint, we were able to find that those 4 patterns on the right were able to make a fitting Kubo matrices. And well, it works. So the idea that we are shipping with constraint learning is something where the user defines an optimizer, so it's slightly inspired by Jump, but just slightly. That is like a subtype of abstract some plugin optimizer, and we can plug it into the compositional networks, Kubo constraints, or maybe future other plugins. So for instance, for compositional network, we have a genetic algorithm optimizer and a constraint-based local search that are currently working. For Kubo constraints, we have a gradient descent and a CBLS, and we hope to add some more. The perspective for the future are basically to cover all core constraints, as I have shown before. Really, we want to integrate with other rated ecosystem package, Jump, Kubo.jl, I need to update my slides now, etc. And we want to add more plugins and more optimizers. For those interested by the theory behind and the experiments, we have 2 related papers that appeared this year, so please have a look.
So in the interest of time, I might ask that we hold any questions for these 10-minute talks to lunch, which is going to be at 12:30. And then I think next up we have, well, at least on my schedule, we have Theo, who's going to be telling us about exact ADMM. Inexact ADMM. I had you down as fast convex optimization with G. Niles. Okay, and so the clock at the back is running a minute slow, so we're actually on time.
Great. Great. Hi, everyone. I'm Theo. Talking about this new solver I've been working on called Genie.OS. Name is still a work in progress, but right now it is generalized Newton inexact operator splitting solver. But in essence, it's inexact ADMM. There we go. So the motivation for this is just how do you exploit more structure that's present in optimization problems. And if we look at some common optimization problems like Huber fitting, which is a robust regression problem, we get these constraint matrices that clearly have tons of structure in them. If we look at Markowitz portfolio optimization, which was mentioned in a talk earlier as well, again, we get this constraint matrix that has a ton of structure in it. And there's a question of like, can we use information that we as the user know about the problem to speed up the solvers? Many solvers, of course, force problems into a very standard conic form that has only a few kind of standard cones, and this can cause kind of an explosion in the number of variables. And of course, if you have a quadratic or a cubic subroutine in this solver, you're going to go from 4x the number of variables, might add 2 orders of magnitude to the solve time. And of course, this means it's hard to take advantage of problem structure if you're just putting everything into a sparse matrix. And so to go into one example, for Huber regression, the details aren't super important, but essentially you have this pretty simple machine learning problem on the left, which is just your standard L1 regularized machine learning problem with kind of a different loss function. And then the equivalent quadratic program on the right is going to have this like, you're going to, instead of optimizing just over x, now you have like x and r and s and t and q, and so you start to introduce a lot more variables. You get this matrix where that A matrix, which is probably going to be a huge amount of dense, potentially dense data, is in the upper left corner, and then everything else is this very sparse thing. So we'd prefer to solve this one if we know kind of a priori. So this solver, Genie.OS, kind of is motivated by this, and we construct it to solve general convex programs. We're using inexact ADMM, so we only actually need function, gradient, and Hessian vector product oracles for f, and the Hessian vector product can be approximate, and then we need function and proximal operators for g. Of course, this can be specialized to things like quadratic programs, conic programs, and then this kind of general form, what I call a machine learning problem, but it's a very specific type of machine learning problem. And we use an exact ADMM for this. So ADMM, I don't have time to give a full overview, but we solve 2 subproblems at each iteration. And what we're going to do is we're going to approximate these subproblems. So we're going to solve approximations to the subproblems. For the first subproblem, we use a second order approximation. The important thing here is first, it allows us to only need that function, gradient, and Hessian vector product in terms of our interface for f. But then perhaps more importantly, it means that this problem is a linear system solve. So we don't have to run like LBFGS. We don't have to do anything, kind of bespoke for that subproblem. We can just put it into linear system solve, and we don't have to assume that that subproblem has a quadratic objective because we force it to have a quadratic objective. And then we need an approximate operator or an approx operator for the second subproblem. But this is something that I won't get into that much in this talk. Then, after we have this, we inexactly solve these 2 subproblems. And as long as we can control the error in these, it turns out that we inherit actually not only the convergence guarantees of ADMM, but actually the exact same rate of convergence. So theoretically, we don't really lose anything by doing these approximations. And so back to this, we can kind of look at, the Huber regression standard form or kind of the natural form on the left, the equivalent quadratic program on the right, and then figure out kind of, so first we solve like very standard, solve the equivalent quadratic program with exact subproblem solves, do the inexact subproblem solves, and then kind of look at the directly solving the problem on the left, which we do through this like machine learning interface. So for that, all we say is give us your loss function, give us your L1 and L2 regularizers, and we'll find the best linear model based on your loss function and these regularizers. And you can see it's basically specified with kind of 2 parameters plus a function that the user supplies, uses autodiff to figure out the first and second derivatives, and this is the per sample loss. And actually, if we supply the conjugate function to this, we can compute the duality gap for this particular type of problem. So perhaps instead of just looking at the primal and dual residuals, you would rather use like a very explicit duality gap and use that as your termination criteria, and that's something that we can do as well. Providing the conjugate function tends to be quite easy when you're dealing with a one-dimensional function. And then the quadratic programming solver just needs the problem data matrices and vectors, and this is easiest. While we supply a native interface, it's easiest just to use jump to supply these. And what we see is actually kind of surprisingly, we can easily get like a 30 to 60x speed up by using the non-native form, or sorry, using the more natural form of this problem versus using that extended formulation as a quadratic program. One other interesting thing here is if you look on the left, we're looking at both the dashed lines are the entire solves and the solid lines are the linear system solves. So when we go to a quadratic program, it actually, the overhead on top of the linear system is greater. And that is because kind of having a dense block and a sparse matrix is bad. And even for things like calculating the convergence criteria on this, we're not able to like use kind of, BLOS level 2 operations that have really, really fast dense matrix vector multiplies. Of course, this is Julia, so we can say, well, why don't we make a custom matrix type here? And I would say that kind of sounds like a lot of work. So it's easier if we can just specify our problems directly. The one other example I wanted to go through is this Markowitz portfolio optimization, which is just solving a quadratic program. The important thing here is the covariance matrix, which is the matrix that appears in the objective, is known to be diagonal plus low rank. And usually, kind of before you solve this program, you have the diagonal and low rank factors of this. So this is something that's part of the problem data. Of course, if you form this matrix, you form a dense matrix, and the solver has no idea that this is diagonal plus low rank. And this is clearly kind of a quadratic program just because it's quadratic objective and linear equality and inequality constraints. So there's a question of how do we take advantage of structure here. I'd say the traditional way, which I'm just glaze over in the case of time, but is to form an equivalent program. You introduce some new variables, very minor in terms of, in this case, we're actually not introducing a large number of new variables, but this isn't a step that most canonicalizers could recognize. This is a step that the user has to do. So you're kind of offloading the burden to the user to do this, even though you're getting a much faster solve. The Julia way is just saying, okay, well, I know that I can multiply with this matrix really effectively, so why don't I, use linear maps, turn F into a linear map, construct this operator, and then same thing for the constraint matrix, and do that. There's an even more interesting way, which is we can recognize that the set that we're dealing with is the simplex, and we actually have very efficient projections onto the simplex, which is the Z subproblem, which is essentially solved by a one-dimensional root finding problem. And essentially, the takeaway from that is it's really, really fast. So we provide an interface that allows you to specify this entire thing, kind of that what I talked about earlier directly. And with these 4 equivalent ways to solve of the original QP, the QP with fast operators, so that's using multiple dispatch, the reformulated equivalent QP, and then the equivalent convex program where we deal with the constraint set directly. And kind of might want to ask how these compare. And you get significant speed ups as you kind of go from one to the other. So forming the matrix is a very bad idea. Projecting onto the simplex turns out to be a very good idea. Even being able to use custom operators, we found actually starts to really improve over solving the equivalent QP as you get to large problem sizes. Cool. And there's code and documentation up. Right now, it is not on the package registry, but it's there. There's the jump interface for QPs. And I'm hoping to expose more and more of like the kind of custom interface of the solver in jump as well. Thank you.
Perfectly on time.
Yeah,
down to the second. So up next we have Benoit, who's going to be telling us about some of his work in polynomial optimization. we're just going to have to do the trick where we wire them up with a mic.
Is working? Yeah, it seems. I have this. No, maybe I use this one. Yeah, that's. Okay. Good. Okay, so I'm going to present the work on polynomial optimization. So this work is funded by the European grant Back to the Roots at Leuven with Bardemore. So in this project, we are trying to go back to the fundamental problems of trying to root system of polynomial equations or trying to find the minimum of a polynomial. But instead of using a way of using Grobner basis and exact computation, we are trying to develop numerical algorithms. And we want them to be numerically stable, because if you just use the algorithm designed for exact arithmetics with floating point, it's not going to be numerically stable. So first I'm going to say exactly what I mean by polynomial optimization. So what I mean is we have a polynomial P, multivariate. So you have in n dimension, and you want to find the vector x that minimizes this polynomial. And so you can also have constraints. So you can have equality constraints, or you can also have inequality constraint, and this x should satisfy these constraints. So sometimes when you do optimization with polynomial, what you want to do instead is to find a polynomial that satisfies some constraints. For example, in control, sometimes you want to find a Lyapunov function that shows that your system is stable. But this is not what we want here. Here we have, when I say polynomial optimization, I mean that we have a fixed polynomial, and you just want to find the variable that minimize this polynomial. And this polynomial, unfortunately, it's NP hard in general. Of course, if these functions are convex and P is convex, then it is a convex problem. But with arbitrary polynomial, you quickly get non-convexity, and so in general, it's not working. And even in the case where you have no inequality constraints and you have actually no objective, so you're just trying to find a number that satisfies this, then you have a system of polynomial equation, and this is already NP hard. But I mean, we can still try to solve it. And I think what jump user would do when they encounter this kind of problem is that they would use IPOP, right? But IPOP is not going to try to exploit too much the polynomial nature of this. And we are going to try to see in this talk whether we can, by exploiting the algebraic structure of this object, to develop other algorithms that can find the global optimum, because IPOP will only find the local solution. So if we try to look at what the Lagrangian looks like, there are two very different ways to do this. So the first is probably closer to what IPOP would do, is to try to find multipliers for the equality and multiplier for the inequality. If you want the multiplier to be free and not have to be non-negative, we can just try to find multiplier and here use squares to make them non-negative. So we can try to find multipliers such that this condition is satisfied. So this would be the KKT condition. And if you can find x and multipliers here, such that this is 0, this kind of satisfies that x is a local solution. But it doesn't tell you that you have a global solution. So when IPOP is going to solve this problem, and it will find this x and this lambda and this sigma, you only have a local solution. You don't know if it's global. Another approach is to try to, it's not trying to find x anymore. Basically, x is going to be some symbolic variable, but instead you want to find, and lambda and sigma now they are going to be polynomials, not just numbers. And you're trying to find a lower bound gamma at the same time. And what you want is that this expression is, this equality holds for all x. So basically, this is a symbolic expression, a polynomial expression, and this polynomial should be equal to this constant gamma. So if you are able to find polynomials here and here, actually a sum of squares of polynomials such that this holds, then what's happening is that you have a proof that everywhere in the state space, for every x, that satisfies that h is 0 and that g is non-negative, p is going to be greater than gamma. So you found that gamma is a lower bound to your problem. And that's a self-contained proof of that. And this is called this counts for the positive Stallensatz, which is a bit more complicated. So this certificate is called the Putinar certificate. And sometimes by doing this certificate, you don't find as a lower bound actually the true minimum of the problem. But the positive Stallensatz tell you that there is you can make this certificate a bit more complicated by increasing. Actually, this one will work in some situation, but you don't know what are the degrees you need for the lambda and the sigmas. You just know that they are polynomials. So you already have a hierarchy of increasing degree that you should need to try, and that will improve the lower bound. But there are also cases in which this certificate is not sufficient, and so sometimes you also need to multiply the polynomial on the left by some additional decision variables. But there is this positive Stallensatz that's telling you that at least there exists a degree if you at which basically this bound gamma will be equal to the true minimum of your program. So that can be an approach. Now, if you do the KKT approach, of course, just trying to solve this KKT system may not be sufficient. So, for example, there are some corner cases like this one. If you take this polynomial optimization problem, if you try to solve the KKT system, you arrive at this system when x is equal to 0, and you see that there's actually no solution. And the reason is that at this point here, which is actually the only feasible point, the rank of the Jacobian is only 1, because the normal vector to both these sets are parallel. And so there is actually, if you try to, and here the gradient is going to be a vector like that, so this vector is not a multiple of these things. So, but if you're sure that you're not falling into these traps, then you know that basically the optimal solution would be a solution of the KKT. And so, actually, instead of, if you want to use the KKT approach, instead of using IPOP, what you could do is actually try to solve this system of polynomial equations. So, if you look at this, basically you have 3 variables here, and you just have here wait, I was missing gradients here, and you never told me. Are you paying attention? So if here you put gradients, you have a system of polynomial equations, right? So you need to derive this by all these variables, right? And here you have a system of polynomial equations. And if you solve this system of polynomial equations, you will have as many equations as you have variables. And if you root this, you are going to get normally all your solution if you are not in these cases, right? And to solve a system of polynomial equations numerically, there is an approach that we are developing, which is to, so the classical approach is basically you look at all the equation of your system, and you know that if all these polynomials are 0, you know that if you multiply this polynomial by any other polynomial, it's also going to be 0, and you can even sum them. And so you can generate many polynomials like this. And if you want generators of everything you can generate like that, you can basically multiply your polynomial by just monomials. And this is going to generate all the polynomial you can generate if you consider all the possible monomial. And if you put them, all of these, in a matrix, Of course, it's an infinite matrix, but if you restrict the maximal degree that you can have in this polynomial, you have a matrix of increasing in size by increasing the degree. And so one approach to solve this system of polynomial equation is to take this matrix and to reduce it with Gaussian elimination, or to do row echelon form. But this approach is called the Buchberger algorithm, but it's not numerically stable. So that's not what you would like to do if you're working with floating point numbers. And so instead of doing this, what you could do is actually do an SVD on this matrix, which is much more numerically stable than Gaussian elimination, and that would be numerically stable. But then what would you do with this? So basically, one object that's important with this matrix is its null space. Because it turns out that in the null space of this matrix, if you have the condition that the rank of the null space is the same as the rank of the null space if you remove all the rows corresponding to the monomials of the largest degree, if these two ranks are the same, then actually you can recover the solution of the polynomial system from this null space. And so this gap condition is sufficient to finding all the solutions. Okay, so if you do this approach, generating this matrix, doing SVD, and you have this gap, you actually found all your solution, and you didn't have to do numerically unstable ways, things such as Gaussian elimination. So it's purely numerical approach. Now, in the sum of squares site, it turns out that what you're doing looks quite different, but you're going to end at the same point. So this time you are trying to generate a certificate like this to show that gamma is a lower bound. So what you do to solve this certificate is that you're trying to solve a sum of square program by trying to find the sum of square polynomial. This can be formulated into semi-definite programming and so on. And then once you find this lower bound gamma, I mean, it's very nice. You can say maybe 3 is a lower bound to your problem. But if you're actually interested in the minimizer, that's not the complete solution, right? So because kind of what you obtained the multiplier, so kind of the dual, but you didn't have actually the primal of your problem. So can you obtain the primal as kind of the dual of this dual? So this you can actually do, but you need to take the duality in the conic form. So if you look at the search for these multipliers as a conic program, and you take the dual of this conic program, you cannot recover what should be your x, but what you have instead of just a vector x is that you have a matrix of moments. So you have a matrix of values for monomials in x. Now, how do you obtain x from this matrix of moments? So there is also a whole theory on that, and it turns out that again, if you take this matrix and you remove all the monomials of the largest degree, if the rank of the resulting matrix is the same as the rank that you had before, you have a condition that says that actually this means that your matrix of the moments can be seen as the moments of an atomic measure, and you can recover the centers of these atoms of this measure, and these are actually your solutions. And so you have a very similar condition about the ranks, and you can actually obtain the solution from these moment matrices. Okay? So that's in these two approaches. At the end, you kind of need to work with this matrix, looking at ranks, and you can kind of extract the solution like that. So here is an example. So if you're trying to minimize the Goldstone sprite function, with just the minimal degree that you can use, you don't need to increase the degree of the hierarchy, you obtain this moment matrix, 15 times 15. And so the rows and columns of this matrix should be interpreted as being indexed by these monomials. So this should be thought of being the moment of the monomial you obtain by multiplying 1 with 1. So that's the moment of 1. So it should always be 1, actually. So that's not very interesting. But this one here should be interpreted as 1 multiplied by x2. So this is the moment of x2. This one here it's 2, 2, so it should be x2 squared, so this is the moment of x2 squared. And so you have all these moments. Now the rule of the game is that you should try to find some measure such that if you do the moments of this measure according to all these monomial, you should guess always all these values. So can you guess the minimizer of the Gaussian price function from this matrix? You can. Now, if you do the flatness condition, all the highest or the monomials are the one of degree 4, so it's the last 5. So if you only take the first 10 by 10 block, if you look at the rank, it's actually rank 3. And if you look at the rank of the largest matrix, it's not so obvious, because if you look at the SV singular values, you have a kind of 2 echelon. But you can interpret it kind of as a rank 3 matrices, and you can sort of use the previous technique, and it's possible. I mean, it's possible to kind of extract it, even if the numerics are a bit tricky. But actually, there is a much more easy way to see it. Is that I told you that this is the moment of x2, and this is the moment of x1. And so, if you want to cheat, you can say, let's say that I take a trivial measure, and I just look at only these moments, and I get rid of the rest of the matrix, right? So then you can finding a measure so that the moment for x2 is -1 and for x1 is 0. It's easy. It's just one direct centered at 0, -1. And it turns out that this is the minimizer of the Gaussian price function. So actually, sometimes you can use simple heuristics to find very good solution. In this one, you can actually get the optimal solution by doing almost no work. And this was suggested by Monique Laurent in her book. So in a sense, it looks a bit like, if you think about what we've done, like trying to find this certificate using sum of squares. We have this positive standard set that tells us that there is a very large degree for which this is equivalent, but because we are doing it for a lower degree, we're kind of solving a relaxation. And so this moment solution is kind of the solution of a relaxation. So what we know very well in this community as a relaxation is the integrality relaxation, when we're trying to solve a mixed integer linear program. And when we're solving this relaxation in a branch and bound, and we obtain a fractional solution, what we try to do is we try to round it into a non-fractional solution. And the way we round it, it can be just any heuristics. You don't need to have any proof that this is a good it's just a heuristic. Any way that round this could be good. If you just saw that in practice, it allows you to find feasible solution with good value, it allows the branch and bound to find good upper bound, and that's only what you need, right? So in a sense, in here, if we just have this heuristic that works well in practice, basically we don't need a proof to tell us that we are going to get the optimal solution. We just need good method to find good solution in practice, because we already have this certificate that rigorously proves us that we have a lower bound. So how we find upper bounds, it can be anything. Once by any way, we find a value such that P of x, the value is feasible, and P of x as this value is equal to gamma, we will know that we have found the optimal solution. But the proof that this is optimal is only contained here. The way we actually find the feasible solution, it can be any way. So there've been all the developments of this sufficient condition and things like that, but we don't really need to have any rigorous way to do these things. It can be purely heuristics. And so if we want to make an interface to do this approach, doing this sum of square hierarchy to try to find this lower bound with the certificates, and then these upper bounds by trying to round these moment matrices, actually it turns out that the design of JUMP is exactly what we need, because JUMP was designed to be a very good interface for mixed integer linear program, and because we're also kind of solving a relaxation and trying to round it to a feasible solution, we have all the elements we need. So as I explained, if we don't have the flatness property, we can still obtain a heuristic that obtain good solutions. And then we need to report the solution. We have the objective bound attribute in MOI. This is perfectly what we need to return the bound obtained by the sum of squares. And then among all the solutions that we will find like this, we will find some solutions that are feasible, some solutions that are almost feasible, some solutions that are not feasible, and we will be able to report them all to the user because we can report multiple solutions, and we will be able to say actually, well, this one is actually feasible, this one I report to you, but actually it's infeasible, it's just I found it. But you can, and in the order of the solution, you can first sort by giving first the feasible and then the almost feasible and then the infeasible. And then among all the feasible ones, you can sort them by the one having the lowest objective value, for instance. So actually, you don't need a custom interface for polynomial optimization. The jump interface is already exactly what you need. And then for this issue of this hierarchy of increasingly large degree, it's kind of tricky because so we know that for any degree, we just need to solve some definite program. So this is polynomial time, so this is fine. But we don't know which degree we need. And when we increase the degree, the size of the program that we need to solve grows exponentially. So usually, for low degree, you will get quickly the solution. But if you increase the degree, it will get more and more difficult. So if you just do a for loop and increase the degree until you find a feasible solution for which the objective value match the objective bound you get with sum of squares, it will usually be a bad approach because the user will at some point see probably a good solution, and then you will see your solver starting to solve a very large SDP, which will either crash because of memory or will be very long, and we just want to control C. And when your solver is killed, then it will not be able to take the solutions anymore. So a better interface is to, when you do optimize, you just solve for 1 degree. Then the user can see what is the bound you obtained, what are the solutions you found, and things like that. And if he wants to be greedy and solve for the next degree, he calls optimize again, and then you solve the next degree of the hierarchy. And so in that sense, the fact that in jump it's not just a one-shot function, it's like a stateful optimizer for which you can get and set things and call optimize, is very appropriate to do these kind of things. Okay, so then another thing that's very useful is that Oscar have just added nonlinear functions in jump. And so what we can do now, if you want to do polynomial optimization, is so let the user create the problem as a nonlinear function, because it's very easy in jump to specify a nonlinear function. Then if he wants to use IPOpt, he can IPOpt, we just get that. But then if you want to use polynomial optimization solver, we'll first try to bridge this into a polynomial function. So we read the expression of the nonlinear function and we try to see if it's a polynomial. If yes, we convert it into a polynomial structure. Then if he wants to use a QCQP solver, like Alpine or Gurobi, then we basically need to transform this into quadratic function. So when you have a monomial that is larger, you just decompose it by introducing auxiliary variable. Then if instead he wants to do sum of squares, then we can do, we have this optimizer that is going to do this hierarchy and use this inner conic solver under the hood. And if instead the user wants to solve this by solving the KKT system and an algebraic system, then he can use this optimizer in PolyJump that is going to create the KKT system, use an algebraic system solver using the interface in this package, and then return the solution back. So what's nice there is that basically you have just one model, completely solver independent model, and then you can use these 4 kind of solvers that are completely different from exactly the same model. You just need to change this one line in jump that specifies the solvers, and all the rest would be done automatically. Now, one thing that might seem weird here is that this bridge can fail. Like, it's kind of weird to create the model in a nonlinear form, and then after that try to convert to polynomial, while it might not be a polynomial, right? So this this might fail. So is that a good design to create a bridge that you know is probably going to fail? Well, actually, we're already doing that, and nobody's complaining. So we have this bridge from quadratic function to second order cone, and this is always failing if your quadratic function is not PSD. And we receive few complaints about that. And actually, we want to continue to do these things, because what we want to do is, when the user gives a nonlinear function to a conic solver, we want to try to do DCP. But if this nonlinear function is not DCP, it will also fail. So are we completely going on the wrong way? Well, actually, I think this is fine, because in jump, remember that the user, it decides what is the solver we need to do, we need to use. We have, like, if the user doesn't give any solver, we are not going to take a default choice, right? So in a sense, the problem is completely specified. The user says, here is the model, here is the solver, this is the pair that I want to use. Do the best to try to make them communicate. So in a sense, if you use a conic solver with a nonlinear problem, we can either say error, like it's not possible, or try to use one of these bridges that may fail. So because this is basically the only possibility we have, I think it's fine that they may fail. Okay, so the last point I want to make is that, so I've presented these two approaches, or trying to solve the KKT system with the Macaulay matrix, or trying to do this sum of square approach. But actually, I show you that at the end, they need to do something quite similar. But I think that in addition to having a similar n, they can kind of work together. Like, they both suffer, for a fixed degree, they are like polynomial, and they use nice algorithms that are numerically stable. But they both suffer from this idea that if you increase the degree d, they are both going to be exponential. So for both of them, you can easily solve the first degrees, and then you just don't want to increase the degree. And you want to know if it's possible to, while staying at low degree, do a bit more work, but not go to the next level. It seems that when you don't obtain your solution, what you obtain in both cases are kind of complementary objects. Like in the sum of square case, basically, you're trying to find these measures that prove that your polynomial is a bound. So you have a measure where the support is kind of pushed to where all the points where the polynomial is very small. And instead, in the Macaulay case, you're trying to find critical points. And the critical points, they can be anywhere where the polynomial, it can even be local maximizer, and it can even be complex solution of the algebraic systems. So somehow, you usually have a small set of solutions because they are only critical points, but they are not at all going to be where the polynomial is small. And so in a sense, what you really want is something that's at the intersection of the two. And what's nice is that somehow this moment matrix, when it doesn't give you a point, it's actually kind of giving you a system which may be like not a system containing just the solution, but it could be like a one-dimensional variety, for instance, that may actually contain the solution, but also other things. And if you intersect with the KKT, because the KKT contains only the critical point, you may actually single out the solution you want. But one thing that's very tricky is that this system is actually very noisy. But because this approach for solving the algebraic system is actually very numerically robust, because it's based on linear algebra, when you can really control the numerical robustness and what's happening, this is actually a feasible approach. And so if you want to, so I'm going to end with this slide. So they're actually, in the implementation, they're actually already kind of sharing a lot of different steps in these different packages. And I think if you want to make this method work and to be also practically useful like IPOpt, you need to find kind of a way to make these two interact. And instead of just doing this one step and going to the solution, and if it fails, you just increase the degree, try to continue in this space and try to go to some kind of loops and try to stay at the same degree, but try to do a bit more work by working together. But I leave the detail for later.
So thank you very much. We might just. So up next we have Mitch, who's going to be telling us about some work that he's been doing looking at GAMS and jump with a particular focus on equilibrium problems.
There is a clicker. It's the same one I have. All right. Apologies if I sound a little weird. I'm getting over a cold. Okay, so I'll be talking about computable general equilibrium models in jump. It's a little weird because I'm a mathematician talking about economics at a CS conference, so I'm going to do my best here. I work for the Wisconsin National Data Consortium, WinDC, and what we do is we create open source models, multi-sectoral economic models from governmental data. Most of these models are in GAMS. They're typically large complementarity problems, like mixed complementarity problems, so they can be hard to solve. The people behind this, Tom Rutherford, he's the director. He's kind of a big name in this field. If you've ever used MPSGE, he's the dude that created it. Myself, I've been with WinDC for about a year, and Swan, our postdoc, she's been here for about 6 months. So we're a small team trying to do these things. Excuse me. Our current workflow, we take raw government data, process it in Python, and currently we throw that into GAMS to create these models. Of course, I would like to skip, definitely take out GAMS, but skip the Python part as well, because that's kind of the power of Julia, is that you can do that. And I've had actually a lot of success doing this, which is very nice. I want to talk a little bit about GAMS, because kind of my whole thing is replacing GAMS. It's old, developed in 1976, has a huge variety of solvers. I think it supports far more than jump. And it is much fast. It's incredibly fast at creating like equations and like setting up the constraints. It's widely used for economics, energy sector, governmental uses. Very, very popular software. It is closed source and it costs quite a bit, but for these kinds of things, cost usually isn't the limiting factor. It's used because it's fast and it's old. It's kind of one of those self-fulfilling prophecies. People use it because people use it. The syntax is exceptionally terse. It's one of the reasons we actually like Julia, because the syntax is similar, like for creating constraints and stuff. Python is not. And there's also these sets, domain checking, and just embedded documentation. Like here's an example. So this is creating a set in GAMS, and the description is included directly in the definition of the set. So when you report this, like GAMS will generate an automatic report, it will tell you what it is. Same when you create a parameter. And the power of GAMS is that the set X and the set Y, mathematically they're exactly the same, they're ABC. This will fail because it doesn't know that X and Y are related. It will tell you there's a domain error. And this is nice because it keeps you honest, which is important for models that are bigger than 3 things. So what I've done to sort of ease the transition for people that use GAMS quite a bit, I've created a package called GAMS structure. It implements GAMS like sets and parameters, mainly on the data side of things. And you can also save and load these things quickly. So we typically have, 100 parameters or something like that, and dump those into CSVs and load them in very quickly. I've also created this thing called GDX.jl. This might be incredibly useful for people that use GAMS, because this will load a GDX file into Julia directly. And this isn't something clever. This is using a package from Python called GAMS transfer. If you use GAMS a lot, I recommend looking into that. It was actually created by the person that used to have my job at WinDC, and then GAMS hired him. So I guess it's a win for me because I got a job. I think is that big enough to see? I think so. On the left here, we have GAMS code. On the right, we have Julia code. But as you can see, the syntax for creating a set here and what I have as a set here is very similar. As you can see the description in the description. And it's sort of like this universe called GU. So it keeps everything and it can domain check. And it's very nice. This is just a basic transportation model. I'm not doing anything fancy here. And then I'll talk about this later. When I get down into the jump part, here I can see descriptions again on variables and variables. Jump doesn't have support for that, at least I don't think so. I'll talk about that more later. The WinDC national model, this is sort of one of our big, actually it's not a big model at all. It's one of our smaller models. 7 sets, 22 parameters, 293 variables, so it's very small. 9 of those variables are distinct. Variables / constraints because it's a complementarity problem, so it kind of has to be the same. And this tracks 73 industries and commodities at the national level. And it solves mostly fine in Jump. There's 1 year, 1997, for some reason. It just gives the trivial solution when it shouldn't. All zeros. Debugging that one. But all the other ones give the same solution as GAMS, which is spectacular. A slightly bigger model is the state level model. And this tracks flows from state to state. So it will take like dairy in Wisconsin, and where does it go? Like, does it go to agriculture in Minnesota? Does it go to like something else? So this work, so obviously this model is going to be a lot bigger. It's going to be at least 50 times bigger, but probably far more, because what we're going to do is we're going to take those categories that are from like the national data set and disaggregate them. So like by default, it's just agriculture. Wisconsin and USDA kind of interested in dairy and wheat and soy, and so break those up. That's where the majority of our work is. If it were just modeling, we'd be done and it would be great. But it's not. And this is the part that might be presumptuous on my part because I'm, naive. So this is something that I miss from GAMS. There's not a lot, but there's one thing. If you have, basically you can do parametric constraints. So this comes up a lot in elasticities for economics, right? Like you'll have one elasticity if a parameter is 0, another one if it's 1, and something else otherwise. In GAMS, they have this $sign operator, which is not intuitive. I would like it to be slightly more intuitive. I'm aware that there are, and this would implement this piecewise function, which is quite nice. I'm aware that there are packages that do this in Julia. It's not in Jump at the moment, at least if it is, that would be great. This is something I'd very much like, and I might try to work on it. I know it's a relatively big ask. And there are packages, but the problem is I'm solving complementarity problems, so I'm going through the complementarity package, which then becomes a whole issue. And the other things that Jump would be missing from GAMS, just descriptions on variables. This one might be actually easier because it'd be just like the access arrays container and automatic solutions reporting. Like when you solve a model in GAMS, it's very easy to get a whole just description of your model. And then those descriptions are on there, so you can send them to people and they'll be like, oh, that's what Y is. It's like some price of commodity. All right, and I think I finished exactly on time, so thank you for listening.
Thanks very much. I think that adding descriptions to variables and constraints would be kind of useful and doable, so we should definitely look into that. What do you need? Just HTML. Do you want to click it? Or, sweet. So up next we have Shivamoy, who's going to be telling us about computing some optimal branch and bound trees.
So hi everyone, so I'm Shuvo, if you cannot say the first name because it's very long. So I'm a PhD student at MIT Operations.
Sorry, could you use the mic just for the
Sure. Yeah. Okay, so let me start again. So hi everyone, so I am Shuvamoy Dasgupta. I'm a PhD student at MIT Operations Research Center. And I am going to talk about something somewhat non-trivial application of JUMP, which is constructing optimal optimization method itself using a methodology called BNB-PEP, and I implemented the methodology in JUMP. So before I start, I wanted to say something fun about me. So I was involved in one of the very first industrial implementations of JUMP. So if you go into JUMP and look into scheduling trains, so actually, the paper that will show up, so it was done by me and my collaborators in 2016. So it was done in transportation industry, which is very safety critical and slow to move. And at that time, I needed convincing, like that, okay, we should use Julia and JUMP. So right now, I am in the process of in another industry collaboration, like in the same industry. And this time, like I noticed that, okay, like I did not have to convince people as much in industry. So it I think, denotes that JUMP has made a significant progress like since then. So I felt that I should communicate this with you guys. Yeah. So, okay. So now I'm going to talk about what I was supposed to talk about, which is branch and bound performance estimation programming. So this is actually a way of generating optimal optimization methods. So I will skip a lot of the details. So if you are interested, so please check out the paper. It's accepted now and published in Math Programming. So what is the core idea? So the core idea is that, like we show in this paper, that if we are trying to find optimal first order method, basically gradient based methods, we can find them by solving certain non-convex optimization problems. And we propose a custom branch and bound algorithms to solve these problems to global optimality. And using this methodology for several classes of setups, we found first order methods that outperforms the existing methods. And another non-trivial byproduct of our methodology is that it can systematically generate completely rigorous mathematical convergence proofs. Okay, so this is the outline. I will give very brief background how it works, some applications that we have found already, and concluding remarks. So background, the key problem in optimization actually is just this. So we are trying to minimize some function. This is our decision variable, and where f, the function itself, lies in some function class. And through indicator function, we can encode constraint optimization problem in this setup too. So in modern large-scale optimization and machine learning problem, the problem dimension n is very large. So to solve these problems, we usually use first-order methods. So these are methods that we can describe or analyze using gradient if it's differentiable, or subgradients if the function is not differentiable. So the classic example is subgradient descent, right? Like we have previous iterate minus some carefully chosen step size, subgradient selected at the previous iterate, and we combine them, we go to the next iterate. But it's only one algorithm. So there are like many, many more. And we can design our own methods, which was the purpose of BNB-PEP. So why first order methods? Because they are extremely scalable and they are very cheap computational complexity wise, and then they can be parallelized very easily. And most popular deep learning algorithms, they are first order methods. So finding optimal method to minimize the given function class can be of importance. So what is the definition of optimal first order method? So we show in the paper that this class is sufficiently large enough to optimize over this. So without going too much into the detail, if you look into the last line, roughly speaking, it means that the nth iterate is the previous iterate minus the span of the previous subgradients that the method has seen, and HNI is the learning rate or step size. So we denote the class of these methods through MN, and all the methods that I showed before, they actually fall in this class. So it's a sufficiently large class to search for optimal first order method. So what is going to change is the nature of the class itself. Like it could be an LP, what is the input that's going to change, like in this optimization problem. So what will change is the function class. It could be smooth, convex, non-smooth, non-convex, and so on. We show that it's actually a min-max problem, where the outer mean is searching for the optimal method, and the inner mean, it kind of represents the convergence rate. So we are trying to find the method with the best convergence rate. So we can show that, like, going through a bunch of transformation, it can be formulated as a QCQP. I will skip all of the detail, because I already see I have like 4 minutes left. But if you are interested, I have actually a YouTube talk where I go into the process of the transformation. So in the end, no matter what you do, based on the function class, it will be somewhat different, but structurally it will look like this. That there will be many constraints that are linear, but there will be some constraints that represent their non-convex quadratic constraints. And if you can solve them, we show that, like, the optimal step sizes that we find, they will be optimal, like exactly optimal in large scale setup, where the problem dimension n is much larger than the number of iterations you will give, which is the case in most large scale problems. So how it works and how jump is used in this phase is we do the implementation using Julia and jump, and the model itself, the modeling part, relies heavily on the advanced features of jump. So what do we use? We primarily use the callback features heavily to modify existing spatial branch and bound solvers. So I will go into somewhat of the details in the rest of the 2 minutes. So these advanced features of jump, they were like extremely handy for me while I was coding up the methodology. So how do we solve this QCQP? So it's a 3-stage optimization problem algorithm. So first stage finds a feasible solution by solving a convex SDP. So basically it means that in this stage we are just trying to find an algorithm which will not blow up in terms of convergence rate. 3 minutes, okay, that's good. So stage 2, what does it do? It does worm starting. Again, like we use the worm starting feature. So this we solve using a interior point solver, and we find a local optimal solution. In the third stage, we worm start again with stage 2 solution and find a globally optimal solution. And this is where we use all the callback features to modify existing spatial branch and bound solvers. So how we do this? So in this phase, like jump was like extremely useful. We compute tighter varied bounds by solving an SDP relaxation. On the decision variables, we find improved lower bounds on the objective value. Again, this was done by solving an through lazy callback constraint method. So then we, at each node of the branch and bound tree, we somehow modify the behavior of the algorithm by using custom heuristics. And also there is this thing called sparsity pattern of the inner dual variables. So here again, like we use like SDP relaxation. So I will give one example. So this is what would be the optimal method to reduce gradient of strongly convex smooth function class. So even though it's like seem like a very easy problem, so actually we did not know what is the best method to reduce gradient norm squared of strongly convex smooth function class. Okay, so I wanted to compare Gurobi versus our algorithm. So what I wanted to say that is much faster. And this is how you can see, if we compare our algorithm on the worst case performance measure, we actually find a near optimal solution like in 10 iterations in log scale. Okay, so last minute, so I will skip like all the things. One nice application that I wanted to end with is that if we have constraint convex optimization problem, and if we are looking for the optimal first order method, so the optimal method was not known, and we found the method recently in a new paper, which we call Optista. And what is interesting is that it also revealed a completely new structure in terms of the algorithm. Like if you look at the previous first order algorithm, they don't show similar structure. Yeah. So I am done. And I hope that you will check out the paper, and I felt that I could not do this, like the implementation without jump. So, yeah.
Shuvo also wrote a lot of the early jump tutorials in the jump documentation. So we were talking about this yesterday, and this is one of the original authors. So up next, now at the right time, now that he's checked his watch, Guillermo is going to tell us about an application of stochastic programming.
Does it have a pointer? Okay. Yeah, my computer clock was in Brazil time. That's why I came here a little bit early. Okay, so today I'm going to talk about stochastic programming application, and the main goal will be to discuss some design patterns useful that I've personally found useful in Jump and would like to discuss with the community. So I work at PSR, same as Joaquin and Rafael. We do a lot of energy consulting and energy modeling there. And one client came with this big LNGC problem. Well, they have a thermal plant they have to operate. And every week they have to decide, well, should I call for more fuel or not? And well, this depends on a lot of things. So like, should they call a big ship to fuel another big ship to serve as a storage for this thermal operator? And they also have would like to do analysis, like should I invest in some small scale? Should I invest in some land storage? Should I invest in other new technologies to make my operation more reliable and to avoid like any extra cost that the independent system operator from Brazil can find me for not having the power at the right time? So depends on a lot of things whether you should call it or not this LNGC to fuel up everything. So for example, depends on meteorographic conditions, depends on the expectations of prices for the gas that you're buying, depends on the decision of the ISO. Is he gonna to dispatch your thermal plant or not? Depends on a lot of things. So one way to make this decision is to define multiple scenarios of all the operative uncertainties that you might have, and do a stochastic programming approach to try to make a decomposition and have a problem based on a scenario tree and derive a risk adequate decision for your particular business, in their case to operate their thermal plants. And well, you have multiple ways to build the stochastic program. One is to build a full tree approach. You can have some like different decomposition strategies and different heuristics. You can do like more commonly known progressive hedging algorithms, and you can do anything that you want in particular to solve the problem. The goal is to have an optimal solution to take a decision. So I'm going to share our experience on some of the designs that we made for the program and then that I found useful over like many projects working with Jump. And so one of them is like pretty simple. It's just, well, have a single struct. This makes things easier downstream for the software development side. Make a big struct of all the inputs of the model. One especially we called collections, with like all of different collections, and the other one with different time series. And these collections and time series have like these kinds of things inside. So some configurations. What is the thermal plant capacity, some ramps, what is the FSRU, the floating storage regasification unit capacity, any kind of parameters that are from your model, and all the time series that are from your model. For example, how much is the buy price if I asked in a gas network, or anything that varies in time. And this is useful to have in your implementation. And then the second thing that I think that is a big point is that we define some actions that you could apply to your problem. So, for example, we had this abstract type that is a subproblem action, and one possible action that you could have in your problem is to like build a constraint and a variable, build a subproblem. Another possible action is when you have stochastic algorithms, it's very common that you only have to update the right-hand side or something like this. You could have an action to make an update. Another action is to get a result. Another action would be to write a result to a file, and so on, so on. So this is only an opinion of a possible design to do everything. And then for each element of your particular model, you could use the Julian multiple dispatch and say, well, okay, now I have some modeling for the LNGC volume. I have to add some variables. I have to add some costs to the objective, something like this. And then I just like dispatch it on subproblem build. And afterwards, I only have to get the result, and then I say, okay, subproblem get result. And like this, you can try to compose more and more things to try to build more maintainable software. In the end, one of the main ideas is that you have like the full model, the full definition of your problem is something abstract like this, like the nomination subproblem elements, and that you could use this later down the line for every different approach that you might have to solve your problem. And so this is an example. It's a little bit small, but I hope you can keep up with me here. This is like the full tree approach. For each scenario, you just like build the scenario, the particular scenario model. We have some non-anticipativity constraints, an objective, we optimize everything, and then afterwards in the problem solution, I just make the same call again. And when you're developing a very big model, it's very easy to forget a small part, like I forgot to implement how to get the result for this particular variable. I forgot how to name, what are the dimensions that I have to name in this other particular one. And so this is just one choice that will help you make the compiler say to you, oh, you forgot to do this. And then afterwards in the code is really explicit when you implement some of these functions and you like return nothing. It's like I am explicitly saying that I don't want to do this for these kinds of functions. And I do find this a pattern that's really easy to maintain. And so some of my conclusions, well, the idea here is just to share with the community some of the design patterns to help build more jump models in production. We do deliver this, and it is a system that it is on a company making real decisions. And well, there are other ideas in the community. I hope that we can gather and discuss a lot of them. Some of them that I noted here, and there are many more that I just found out about Syntef yesterday, but I bet that there are many more. One is power models, the other is power simulations, Gen X. Well, there are many ways to declare very big real applications in real models, like production models in Jump. And well, we still have some small pain points. One is like a more meta thing, like I'm not yet sure what is the best way to test implementations on very big models, like how to do unit testing. You could do unit testing on like small utilities functions, but how to test models in a broader way, this is still an open discussion for me. And another thing that I do think that is a kind of a pain point is that we do tend to package compile everything and ship as an executable for our clients. And I haven't found a way to like make this very efficient to change solvers in this way, apart from shipping every solver with it, which is not the best solution in my opinion. So that's it. Thank you.
I think the question on how do you test and implement a jump model and check that like what you wrote down is what you intended to write down is definitely an open question that we should think more about.
Maybe the answer is there's no way. I'm more and more thinking about this, and I think that, well, the implementation is the implementation. It's like something self-contained, hard to test.
Can we all thank Guilherme again? So unfortunately our next speaker could not attend, so instead of the advertised talk, we've actually roped in Josh to come and tell us a little bit about some of his work on infinite opt.
Cool. All right. Yeah, I made the mistake of commenting to my wife when I flew in that I don't have to present at this conference. And I was so very excited. But that is okay. I'm happy to talk too. So I'll be talking just a little bit today on some recent progress we've had with infinite opt. I'm also tagging on disjunctive programming, which is a package really led by Hector Perez. That's now he's now at Relational AI. They're really big proponents of JUMP over their math opt interface, so that's been kind of fun. So we'll just go into it. So infinite opt. I'm the infinite opt guy, so that's what we're going to talk about first. For those of you that aren't familiar with this little thing I do, I'll give just a few introductory slides. So infinite dimensional optimization. It has going to have kind of 4 core elements that I'm going to, using my own definitions that we're going to talk about. The first is that of infinite parameters. So these are essentially parameters that index your variables. Think of time, space, uncertainty, and how these can index the decisions you want to make. And these are typically over uniform, kind of a continuum, giving you sort of a continuum or infinitely many decisions you have to make. Okay, it can also have then infinite variables. These are the variables that are indexed by the infinite parameters. So think of like a variable that's a function or indexed, if you will, by time and maybe uncertainty in this case. Okay, we can have differential operators as well. In general, most often we'll be thinking of like partial derivatives or regular derivatives. You take it with respect to time or whatever. And you can use these to create like PDEs or ODEs or whatever you have going on. And then we can have measure operators. So think of like expectations or integrals, risk measures, and how these can kind of summarize over these domains, time, space, uncertainty, that sort of thing. So what I kind of developed was sort of a unifying way of thinking about these types of problems with these sort of 4 building blocks, and how when we do that we can capture formulations in dynamic optimization, space-time optimization, stochastic optimization, maybe combinations of those, and kind of just one abstraction to sort of represent them all in the same place. And this was kind of fun because it can help us kind of capture a wide envelope of different applications and start to kind of cross things over in some different ways of doing it. And so this is what infinite opt seeks to do. And so it's implemented in Julia, of course. That's why I'm here. And it extends JUMP to have these sort of 4 core modeling elements. Some things that I think distinguish it from some other packages out there is for these types of models, it's quite performant in expressing these types of models and transforming them. It also has very extensive documentation. I don't think I can quite match the 1,000+ pages that Oscar and others have put together, but several hundred for sure. And then I would argue it gives us a pretty intuitive syntax. So we can directly embed expectations and derivative operators to really compactly express PDEs and integrals and all kinds of things in a very nice way that Julia lets us do. And it's been used by more people than I originally thought it would be, which is nice. One of the more bizarre applications I heard of, or guys, cool applications I heard of, was talking to some evolutionary biologists that ran across this to start doing like optimal path problems to try to figure out how, if you solve an optimal path problem, how that would compare to the paths chosen by animals as they evolve and that sort of thing. Unusual, but kind of fun. And then the nice thing about using Julia, of course, is as we get to play with macros, we can have some really nice compact syntax. Basically just takes the math and I think gives us a code interface that's pretty close to what the math looks like. Which has helped me a lot in my teaching to basically take undergrads and have them solving like dynamic optimization problems in a few days. So I can actually take my process control course I teach. I'm a chemical engineering professor, and we can solve like monopredictive control problems in one lecture, and most of the undergrads seem to get it, so it's kind of fun. Okay. Anyway, so last year, let's go talk about some progress now. Last year I talked about how I kind of came up with a hacky little nonlinear interface that would allow us to have first-class support for nonlinear expressions in JUMP. For those that are familiar with JUMP and its sort of legacy nonlinear interface, you would know that if you had to do it extensions, it was very painful or not readily possible. We'll leave it at that. So I came up with my own sort of nonlinear object, NLP expression, that InfinOpt used to represent nonlinear expressions. And then these would get translated to a Julia expression tree that could then be taken into JUMP with the raw expression interface. Had a few little hacks in between to make it work. And it worked, yeah. So basically we had this kind of tree structure and got going. The big takeaway from doing this, though, was it allowed us to use like the @constraint macro, the @objective macro, to define affine, quadratic, and nonlinear expressions all in one place. You didn't have to have the special NL macros, which are not extendable for extensions anyway, and allowed us to do that. And you could do deletion and all kinds of cool things and get first-class support. The update now, as Oscar is going to talk about later today, I believe, he's been working a lot on a new interface in JUMP using this nonlinear expression object, which is hopefully going to allow us to have first-class support for nonlinear expressions in JUMP directly that is extendable and can be used by packages like mine. So I've been working on sort of a pull request to try this out and see what happens. Really cool thing as we've done this, though, is we've been able to take away more than 2,000 lines of code, simplify the code base quite a bit, which is nice. Another thing that's happened is with 3 benchmarks I put together, we've been able to drastically reduce some of our model building time and get rid of a Stack Overflow error from some recursion things. So that was nice to get rid of as well. So this looks like a pretty big win, and I think the future looks pretty bright for nonlinear JUMP. I'll leave Oscar to talk about that some more later today. Also, just a quick update. Last year I talked about this big overhaul of essentially our whole data structure to allow for more general transformations of problems. So essentially the idea is InfinOpt should serve as a way to represent infinite dimensional problems. Currently we're sort of married to doing discretization type solution methods. We're working on a more general interface to do other types of things. It's still under work. It just, as it turns out, to do a fundamental rewrite takes a while. So we're working on that. All right. Shifting gears just a little bit, disjunctive programming. So this is mostly been developed by my colleague Hector, and I'll just talk a little bit about that. So for those of you that aren't familiar with this notion of generalized disjunctive programming, this mostly comes from chemical engineering, where we just weren't quite satisfied, I guess, with disjunctive programming, so we had to change it a little bit, mostly to handle nonlinear modeling a little bit better that comes up in our application areas. Here, essentially, the idea is you have these disjunctions. So essentially, you have a collection of constraints with this indicator variable that's a Boolean, true, false. And if it's true, the constraints are enforced, and if it's false, they're not. And you have a disjunction of these, so you typically only have it such that only one of these is enforced if you have several disjuncts. So, well, this comes up often in our domain is expansion planning. So here I could build one plant with all the constraints that come with that, or maybe instead I'll build a whole bunch of smaller things with the constraints that come with each one of those. I'm only going to have the constraints enforced for each group if I decide to build the respective system. So this is an example of where this tends to come up. And we often have logical constraints that use these indicator Boolean variables to enforce a logic on how we go about building these things or enforcing these constraints. There's a nice implementation, Pyomo. It's not the most performant thing ever, but it has a lot of capabilities. And disjunctive programming, which I'm talking about today, of course. This is just basically the same thing. I'm stealing some slides from Hector here that basically gives the formal definition of what this is. I'll just skip over that, but it's there. A big takeaway, though, is the nice thing about modeling with GDPs is it gives us a nice general framework to represent decision-making with logic without explicitly using a bunch of big M's and these types of formulations directly, where we can just use these disjuncts to encode the logic we want to do and the propositions, and then we can apply general transformation techniques, kind of turn the crank, and convert these into MIPS. So one way to do that is you can turn the crank, convert it into a big M formulation, or you can do a whole formation which is going to be in general tighter, but introduce more variables. So there's just different transformations you can do that have their pros, their cons. But the nice thing is you can have just one formulation in GDP, turn the crank different ways, and have different ways of solving the problem, different MIPS with different pros and cons. Okay, so this is a problem that he has. Here's technology selection. This is a chemical process. Again, I'm a chemical engineer. So we can have two different reactors we can make. If we have reactor 2, we can then have two separation things that happen afterwards to separate the products that come from that. A thing my colleagues are working on is this idea of nested disjunctions. So you have here a disjunction, and inside this disjunct, you have a disjunction. Basically, we can build either reactor with the constraints that come with it, and if we build reactor 2, we can either build this separator or this separator. So you have disjunct inside a disjunct. You could also reformulate this as just a non-nested disjunct, but he's proven that if you can do nested disjuncts, you can get provably tighter transformations that happen as a result to get better relaxations. Anyway, so this kind of highlights disjunctive programming where it was. So here you define a model, add in some variables that you want to use. You create constraints that are going to end up inside these disjuncts here inside this block. And then you can have this disjunct macro and kind of put them in this syntax. Not the prettiest thing ever to represent that inner disjunction, and then you can start to put more things inside of it. And then you can reformulate it here for things of your choice. So this is where disjunctive programming was. And I think this is just continuing the syntax here. So we're doing nested, so we did the outer, and now we're doing the inner. I'm going to move on. But some key things that came up from this as I started talking to Hector was that syntax was okay. Still a little clunky, perhaps, relative from the math into how you put it in. Also, the way he had it implemented is it was just directly modifying the jump model as you would do transformations. So you could do like one transformation, but then if you wanted to do something else, you'd have to completely remake the model because it had a lot of destructive additions and changes to the model. So Winter was quite not very performant as a result. And so if you wanted to scale it to a large number of disjunctions, it would scale to like order n to the 4th or 3rd. So not great scaling. I also, as it will become clear in a second, was incompatible with infinite opt, which is the motivation I had. And because of the limitations of jump, we couldn't do nonlinear stuff. But we've been working on a rewrite to address all of those things. So we're working on a new workflow where is basically how it works is we're going to make it so it works with abstract models, not just jump models. It'll also work with infinite opt as a result, where we augment them in the extension field with GDP data, which gives us a place to store all the additional modeling elements that would come with a GDP representation. And then we can transform the model using a solve hook function that's built into it to intercept the thing, do the transformation, and you could do it, call it as many times as you want to different transformations in a non-destructive way to the model. And we'll have a better syntax, and we've been playing around with a new nonlinear interface so we can actually support all these different types of expressions that we'd want to do, especially as chemies, where we want to do nonlinear modeling all the time. So this basically is just a simple disjunct, and this is just code on the side to prove that it works. This is the ugly functional form. So this is just like calling build constraints and all that sort of thing manually, but it shows that our code is currently working. I threw this together about half an hour ago, so excuse the roughness of the slide. But this is where we want to go. So I'm halfway through finishing this. Well, basically what we're going to do is you declare a GDP model, have your variables as you would normally do for your model. You can create a constraint normally, but then you just add on this tag, like maybe called disjunct constraint, still name pending. And then what it'll do is it'll make it so it doesn't actually add that constraint to your model. It gets saved somewhere in our extension field. And then we can use those specialized constraints to be stored inside of disjuncts that we create inside of a disjunction. So they get kind of created in a special way that it doesn't get directly added to the jump model, but will get used as we do the transformation and add and build our MIP. And this will allow us to resolve the model as many times as we want, to as many different transformations as we want in a very performant way that overcomes a lot of the previous limitations and gives us a much more compact syntax, which I'm currently tweaking, so this might change a little bit. But that's the idea. Yep. Now tying this back into infinite opt, a thing I've been working on is what I call event constraints. If you want to talk about this later, I'm happy to. Basically what the idea is we generalize the idea of chance constraints, but to be used across multiple domains. So you could have like a time-valued analog of a chance constraint over time or something to give you some nice relaxation things. I'm not going to spend time motivating that, but we can talk later if you're so interested. Essentially, what this led to, though, is it turns out these constraints I've been working with can be formulated as an infinite dimensional GDP. So essentially here we have disjunctions now that have infinite dimensional variables inside of them, or infinite dimensional constraints. And you can have infinite dimensional Boolean operators. Currently how I handled this before is I would take my infinite model, discretize, then do GDP that works on discrete models, and then do it. The problem with that is if I have some optimal control problem of, say, maybe like 4 infinite dimensional constraints, I discretize it over 1,000 time points, and I get 4,000 constraints to then do these formulations over. But if I could do this in the infinite dimensional form, I could have 4 constraints that I then reformulate, and then I can transcribe, and it ends up being much more efficient to do it that way. So for our new rewrite of disjunctive programming, it's going to make it so we can create a GDP model but pass an infinite opt model, and then basically have the same syntax, and we can take advantage of these performance things. So anyway, again, syntax being finalized, but that's the idea. All right, that's some updates in a kind of a rambly fashion, but that's what I got.
Thanks. So are there any questions or Joaquin?
Have you thought about creating
a
kind of a set that is a disjunctive set? So you can add like vector of defined constraints kind of thing, and that would be one of the sets that you can do everything in the MOI level.
Yeah. So the question is, have we thought of just using MOI sets instead of, and go down to the MOI level instead of doing this kind of more at the jump level, right? Essentially, right? Yeah. The short answer is yes. Some of the motivations to the jump level instead is it's a little easier to kind of get our feet wet and to prototype. The other reason, though, was as we started getting into what we really care about, like these nested disjuncts and things, it gets pretty nasty to try to figure out how to represent that at the MOI level and then try to have bridges that work effectively and to call that. So trying to get that whole workflow to work effectively, perhaps it is possible. I couldn't quite figure it out. And so to have a way that we could call different transformations by the user on the fly over and over again in different ways and have nested disjunctions with like nested sets, I'm not sure how you would do that in MOI. So that's why we're not doing that. We can talk afterward, though. Yeah.
Yeah, so it was approximately the same question. One thing I was wondering is the fact that you're doing at the jump level easier if you want to interface with infinite opt?
Yes. Yeah, it makes it a lot easier if I want to interface.
And I've always been interested by how you combine two jump extensions. Because, for example, here you have a solve hook, but does infinite opt also have a solve hook?
Infinite opt does not have a solve hook, so it's an extension. Because infinite opt, right, is based off, I think it's the only extension that actually tried to implement an abstract model, so it's its own thing. Warning, you can do it. It's a lot of work. I'm not sure I recommend it, but I mean, infinite opt is nice as a result. Whereas, yes, GDP is doing the idea of you just have extension data and you do the solve hook. If you had two extensions that try to do the same thing, yeah, that doesn't really compose. So this goes up to another question I had on my last slide I forgot to really talk about, was this idea of composability. Like, what are some better ways where we could think about making it so jump extensions are more readily amendable to being composed together? It's kind of an open question, I think. And then one of the ways we recommend to extend jump, right, is you can add tags to like variables or constraints. So I'm using this right now with infinite opt as part of my rewrite. there's a number of situations where I have multiple tags, and then the combinatorics of different tags becomes a bit of a nightmare to kind of make composite types. So coming up with a better way of handling that is also an open question.
No, we also have the in syntax when you create variable.
Yeah.
Like in Polynomial, we also use tags when you say actually this variable is a polynomial.
Yeah.
But I think now that with the in syntax, it's a bit nicer to say add variable x in the set of polynomial that x comma polynomial. I don't know.
Yeah, so you end up using like a set type thing.
Yeah.
Yeah.
Any other questions?
There's a relationship between the disjunctive programming and complementarity. Do you have
They are
complementarity?
So complementarity, the package?
Constraints in general.
Constraints in general.
Yeah. Do you handle anything via complementarity constraints?
So currently, the way this is built out is it, in theory, will accept abstract constraint objects. I probably should be a little more judicious with my checks. So if when you add that abstract constraint object ultimately to your jump model, if your jump model knows what to do with that, you're good to go. If it doesn't know what to do with that...
I guess the question is also, could you reformulate?
Oh, could you reformulate into something else?
Disjunctive.
I see. Yes. Yes, yeah, mathematically, yes, you totally can, yeah. So the question might be, can you reformulate complementarity constraints into disjunctive programming or vice versa?
First question, yes. Is that true?
Yes. Yeah, mathematically.
The second question is, do you do that somehow? Is there any code that does such things in your scheme?
Like to like references. So the question is there a way? Do we have code built in to like take you specify a complementarity expression and then convert that into a GDP? Is that the question, or vice versa? Yeah. So as we're building out some of these logical propositions and things, one of the operators we plan on supporting is complementarity. So yeah, it's a work in progress. Yeah.
Anything else? Should we thank all of the speakers in this session? The plan now is everyone is released for lunch, and we're meeting back here at 2 o'clock to carry on. So welcome back, everybody. We have another hour and a half of talks in this session, all kind of loosely related to nonlinear programming and a couple of other things. First up, we have Tanguy, who is going to tell us about Julia Smooth optimizers.
Thank you, Oscar. Okay. Oh, do you hear me well? Oh, awesome. Thank you. Well, thank you, Oscar, and thank you for all the Jump Dev organizers to give me this great opportunity to talk, to tell you some of the things I'm interested in, and for organizing the day of super interesting talks in general. And so today I'll talk about optimization solvers in Julia Smooth optimizers, which is also a GitHub organization which is sort of complementary to what Jump is doing, except that we are really focused on developing solvers. Okay. So this is joint work with Dominique Orban, Abel Siqueira, and others. I'll tell you about. Oh yeah, thanks. In a few slides. Okay, some preliminaries. So in general, I'm interested in nonlinear, non-convex optimization, meaning you want to minimize or maximize some function. You have constraints that are described by inequalities and bounds. And the algorithms I'm studying are always based on computing derivatives, so I will assume that everything is smooth. And if I tell you that I'm solving something, it's usually trying to find a local minima or satisfying some stationary conditions. Okay? So nothing too surprising for you, I'm pretty sure. And to tell you a few more words about Julia Smooth optimizers, our scientific background is numerical linear algebra and optimization. So I told you already, it's a GitHub organization, and that was first initiated in 2015 by Dominique Orban and Abel Siqueira. And the first packages were qtest.jl, AmpleNLReader.jl, Krylov.jl. And the core contributors of the organizations are researchers in these two fields of numerical linear algebra and optimization. Okay? And so in particular, that means that we want to write research paper, studying algorithms, playing with them, and also studying. Okay? So everything that I'm presenting to you today, we also use that with students. We ask students to write solvers, make benchmarks, and everything like that. Okay? Awesome. I think my talk is also a good follow-up of last year talk about Julia Smooth optimizers by Dominique Orban. I'll let you review that if you want. And now we have a new fancy website called jso.dev. Okay. So since Julia Smooth optimizers, it's like too long for me to repeat 100 times during this talk. I'll just say JSO. Awesome, and so since 2019, to give a few words, there has been 21 journal accepted publications and a book about JSO packages or using JSO packages. And it's now about 50 Julia packages plus a dozen not registered packages, so it's starting to be really crazy to maintain. And in my talk, I will only talk about the smooth nonlinear optimization part. So nothing about linear algebra, and also there are some new packages on non-smooth optimization. So awesome, and to give you like a slightly outdated table with all the packages classified in category, here it is. So you'll see there are packages about modeling problems, solvers, wrappers with existing solvers, linear algebra, and some other really nice things, like we have a lot of test problems packages and some various tools. We are really dedicated to make the packages as good as possible. So we have a lot of things for unit testings, test problems, and so on and so forth. Cool. So some motivations about my talk. So JSO has become a very large organization with multiple options for each covered problems, meaning for each problem now we're starting to have several algorithms. And it might take some time to find the right modeling tool and the right solver. Like if you don't know anything about JSO, like you would have to find what's the right package for your solver and everything and so on. So we needed, I think, a tool that gives a simple and intuitive entry point to the JSO universe. And also that tool would have to be sufficiently nice to easily prototype and compare solvers to find the right option. Okay? And I believe the answer to all these observations is what's called JSO Suite.jl. So the package's registration is ongoing, so the name might change a bit, but the spirit will stay. Okay. Cool. So I know you like codes. I don't know if black was the right color for the background, but you should manage to see it a bit. So essentially what we would like to do is just ask the user to give us a function, an initial guess, and then say, oh, I want to minimize this, and bam, okay? Or maybe the user actually wants to do all this in single precision in float32, and then he will give us a float32 vector as initial guess, and I want to do everything in float32, okay? And the same with constraints. So the rest of my talk will be a bit to explain what's behind all that. Okay, and so first part in this is that you have to modelize the problem and then you have to solve the problem. So I'll talk about the modelization part first. And the specificity of Julia Smooth optimizers is all in one of our core package, which is NLPmodel.jl, which provides a standardized API for general nonlinear non-convex optimization problem of this form. Okay. So you give me an objective function, and then you give me a constraint function to describe your constraints and eventually bounds. Okay. And what NLPmodel.jl does is that it provides a list of methods that you can rely on to access this problem. So typically things that we want to do, we want to evaluate the objective function, but also compute its derivatives, do the same for the constraints, and maybe you don't want to have the Hessian matrix, but just want to do Hessian vector products, and so on and so forth. Okay. So a small add-on this is that you can also actually define separately linear and nonlinear constraints, which can be convenient sometimes. Okay. Cool. So as I said, essentially you want to access derivatives, and we see it as two ways. Either you want to compute factorizations of some system involving these matrices, so that you can access the Jacobian and Hessian as sparse matrices in CO structure, or maybe you want to derive a factorization-free method and then just want to access a matrix vector product. Okay. So you can this either by accessing the hprod or jprod function, or you can ask the NLP model to give you some lazy matrix structure via linear operators. Okay. Awesome. And so actually NLPmodel.jl does not do anything but describing these abstract functions. Then you have to implement them as some concrete model. So I'm sure for all of you, the intuitive way would be to build a jump model, and then you would call NLP model jump to just squeeze the jump model as in the NLP model API. So that works really well. But you can also do other things, like we have one package called ADNLP model. I will tell you more about this one in a moment, that use automatic differentiation. You could give us the function by hand with manual NLP model. And why we need this NLP model is also to adapt to some specific situations where you know more about the problems. And that's why we have, for instance, PDNLPmodel.jl when designed for PD constraint optimization, and maybe you have a finite element discretization of your PDE, and you want to use that to access the derivative and build your discretized PD constraint model, and so PDNLP model will do that. Okay. And same thing would happen for other examples. Here I noted partially separable NLP models and other wrappers with machine learning systems. Okay. Cool. So a few things I won't talk about, at least not for a long time, is that you can also specify your problem, for instance, here with nonlinear least squares, where your objective function is actually the square norm of some residual function, and maybe you know that some algorithms specified for this, such as Gauss-Newton or Levenberg-Marquardt algorithms, they will want to rely not on the Hessian matrix of this objective function, but just on the residual and the derivative of the residual, okay? So that we extend the abstract NLP model API to this case so that you can also access the derivative of this, and then your algorithm can access this, okay? Another really interesting thing with NLP model is that you can also very easily transform your problem. In case you have read some research paper about algorithms, very often they tell you, oh, we can solve the inequality, but first you have to write the problem with slack variables. And then you start to think, oh, wow, I'll have to rewrite the whole thing. And with NLP model, then it's just a one-liner thing, okay? So we, in the package NLP model modifiers, we have a set of transformations like this that does everything for you. Cool, so that's sort of a brief overview of some of the capabilities of NLP model. And now I want to say a few more words about AD NLP model. So the AD stands for automatic differentiation, and that's a great one because it doesn't ask much. The user can provide a Julia function, and that's it, okay? So the great part about this is that you can use any floating point type that support arithmetic operations, and essentially we use as base forward diff and reverse diff to compute derivatives, okay? And so actually that's just the default. We also provide derivatives with other packages. I'll give you an example next slide, okay? And so the package was designed with a backend organization of the different functions where we need automatic differentiation. So it's super easy actually to build one model and compare two AD systems and switch AD system and so on and so forth, okay? And one of the recent add that was, I think, really important is also to add sparse Jacobian and sparse Hessian computation. Cool. So yeah, to give you a slightly more concrete example, so here I would define an AD NLP model and not the exclamation mark. It's because I'm specifying here that the constraint function will be an in-place function. That's usually very useful to save allocations later on. And so that's pretty intuitive. I think you would have to give the objective function, the initial guess, the constraint function, bounds for the constraints. And then that's what I said with the backend system. So in the NLP model API, you have a set of operations. And here, for the gradient, I will want to use enzyme to compute the gradient, forward diff to compute Jacobian vector product, and reverse diff to do the transpose Jacobian vector product, for instance. Okay, and if you want to compare then Jacobian transpose vector product here, you could just switch the backend, okay, as you see as that. And so we also define some shortcut, so it's in green, maybe you don't see it, but just instead of specifying all the operations, you can just say, okay, let's do the optimized backend or the default backend. Awesome, and then another really nice companion package for AD NLP model, and I think it's also interesting for JUMP, is a package called optimizationproblems.jl that contains a list of close to 400 problems in JUMP and in AD NLP model format. Okay, so we use this one to do a lot of benchmarks, and the package also provides a meta in a data frame that gives you all the informations regarding the problems that are there, so that's good to select problems beforehand without having to load them. And if some problems are nonlinear least squares, then you can ask for an AD-NLS model instead of the AD-NLP model, so then you could access the residual directly if you have an NLS solver. And among these 400 problems, about 100 are scalable, meaning that depending on some parameter, you can sort of choose the number of variables and the number of constraints. Okay. And for if you are interested in contributing to this, we maintain list of issues with problems that we are planning to implement, or you can add the ones you are interested in. Cool, and then we could derive stuff like this. So this is one benchmark among many others that we could do. It can be useful, and it will be no surprise that usually jump is doing really good. And then you can see differences when you use reverse diff for the gradient compared to forward diff to the gradient, which is no big surprise, I think. Okay, and then you could derive this for more problems. So that's on 95 problems from optimization problem.jl, where you can change the number of variables. Okay, cool. And another really interesting features, and actually that's one of my strong motivations in ADNLP model, is the possibility to create mixed NLP models. So let's say you have some very nice application with some structures, and maybe you know the Jacobian matrix, maybe you know the Hessian matrix, but don't want to compute optimized Jacobian vector product, Hessian vector product, for instance. And that was my case in PDNLP model.jl. I know how to compute the Jacobian, but then to compute Jacobian vector product, I had to reevaluate the whole Jacobian, and that was painful and not that useful for my case. And so instead of my backend, I can, instead of giving a backend to compute the derivative, I can actually give as a backend an other NLP model. And then instead of using automatic differentiation for this backend, it will use the existing model. Okay. So then with the construction I'm showing here, so the model on line 2 is importing one of the PD constraint optimization problems that are defined in this package. And then, okay, so that's just a bit of rewriting of the objective and the constraints. And then most important is on line 13 and 14 that I'm saying, oh, Jacobian backend, actually you can take the original NLP model. Okay, and so the resulting NLP will have optimized matrix vector product with automatic differentiation, but will keep what I know from the problem. Okay, so I think it's pretty cool. Great, so that explains most of it for the modeling part and some of the progress with ADNLP model. And so now what you will ask is how we solve this problem. And in Julia Smooth Optimizers, we have something we called JSO compliant solver. So it's a set of rules. And if you satisfy those rules, you have a JSO compliant solvers. And actually, there are only 2 rules. You need to accept an abstract NLP model as input, and you have to return a generic execution stat. So that's just some structure we define with some basic results from your optimization. Okay. And that's it. And what I think is really great is that then the solvers you defined, they rely on the NLP model API, but they don't have to know anything about the model. Okay. So if you have a PD constraint optimization, or if you have some nonlinear least square, they can they all implement the NLP model API, and you can use the same solver. And so as I said, the list of packages on solvers is growing. We have wrappers to existing solvers from Nitro IPOpt via actually the jump IPOpt.jl and Nitro.jl. We have also wrappers to AlgenCan, thanks to Paulo Silva, and some homemade Julia implementation. So here I'm mentioning a RibQP, which is an interior point method for quadratic programs, and then some solvers for nonlinear optimization like Percival.jl, which is an augmented Lagrangian method, and DCI solver, Fletcher penalty solver for equality constraint right now, but this will be extended soon, I hope. Awesome. And so to talk slightly more about JSO Suite, so back to this very generic package. So JSO Suite will first define a data frame with most of the information you would like about the different solvers. So here I just truncated the columns. You have like 14 of them. And so these are the 13 solvers that we have in JSO Suite. and you would have some name, the name of the package, and other columns would tell you if it uses second order derivative, if it's compatible with bounds, and so on and so forth. Okay, so that you don't have to know anything about the solvers to start exploring what are their capabilities. And then JSO Suite first method will select optimizers, so that you would define your NLP model and then pass your NLP model to select optimizers, and it will start to analyze it. Like basic things would be, okay, first determine if the solvers that are adapted to your problem, is it unconstrained, is it bound constrained, does it have equality constraint, and so on and so forth. And then check if it's nonlinear, check if it can use second order derivative or only first order derivatives, and then gives you a list of the available solvers. Okay, and then you can just call the solve or minimize here and solve the problem. Okay. So that's pretty cool. And so at the same time, we are trying to maintain a list of keywords arguments that are common to all the solvers. Okay, so that we will do the conversion in stopping criteria for you, which is I think good. Great, and one slide I'm particularly proud to show you, and as usual, sometimes a lot of work is summed up in 8 lines of code. So you can also use an in-place solve for your solvers, and that's particularly useful when you have a loop, for instance, and you want to solve again and again the same problem. You don't want to reallocate memory, you want to reuse the same memory. And so we have the solve exclamation mark. And what I'm trying to show you on this slide is actually, so I'm solving some problem with Percival, and we are seeing that resolving the problem doesn't allocate anything. Okay. So actually, you see on line 2, I'm defining an NLP from NLP model test. So this package contains, in particular, a list of problems where accessing the model doesn't allocate anything. Okay. And so here I'm really testing what the solver does, and so the solver structure contains all the memory that you will use during the iterations of the algorithm, and stat is the structure I told you about that stores the results, and so calling solve should do the trick. Okay, and I think that's kind of impressive because Percival, it's an augmented Lagrangian method, so it iterately solved unconstrained or bound constrained problems, so these solvers are also allocation free in this sense, and these solvers called Krylov methods also that are also allocation free in this sense. Okay, so a lot of solvers satisfy this. Cool, and so that's essentially all you have to know to use JSO. The last bit, since we are researchers and we want to write papers, study algorithms, compare algorithms, is to do benchmarking. I'm just giving you a list, link to some benchmarks where you could see, and believe me that it's just like 10 or 50 lines to do a benchmarking to generate performance profile. And I thought I'd give you one example. So here I took problems from the collection of problem Q-test. I've selected equality constraint problems, so there are no bounds, just equality constraints with up to 10,000 variables and 10,000 constraints, so that gave me 82 problems. And I tried to compare here IPOP, Nitro, and DCI solver, one of our homemade solvers. And so DCI is in green, and it's doing, I think, quite well, comparing that Nitro and IPOP have been there for decades almost now, and are well-studied solvers and well-optimized solvers. And actually, I think the figure on the right actually shows that we have some margin in probably parameters of the solvers to avoid doing unnecessary stuff. Okay, so these are Dolan and Murray performance benchmark performance profile. Cool, and so I can go on and on. This would be another benchmark. Here I'm comparing unconstrained solvers on 80 problems from optimization Plasmo.jl, and the computations were done in float 32, for instance. So you see that the number of problems solved is a bit smaller because, again, probably parameters were not optimized for the single precision. And yeah, and one last benchmark that one of the students in our team in Montreal sent me, Geoffroy Lecomte, who is a PhD student and developer of RibQP. So this is the kind of algorithms we are also super interested in. It's what we call multi-precision solvers or mixed precision solvers, so that first it does the first iteration in float 32, and then when it judges that it's useful, it switches to float 64, okay? And so the line in red would be this multi-precision strategy, and the line in blue would be just using float 64 all the time, okay? And that's the kind of progress we are hoping to get. And as you see, what's funny is that the float 64 only version solves more problem because switching precision always comes with some risks. Okay, so some work still to be done there. Awesome. So to conclude this presentation, I wanted to emphasize that Julia's Smooth Optimizer's NLP model API was first designed to solvers, and now we have a list of so many solvers that are great, I think, but it's really difficult to access, and so JSO Suite was the solution to bring JSO optimization facilities to the rest of the world, essentially, okay? And I believe it's becoming a real good tool to prototype and choose the most adequate optimization solvers. So it's at a pretty early stage right now, but the goal is to make it a sort of a pedagogical tool, okay? So what we are learning in a numerical optimization class, that you have to use this solver in this case, and so on and so forth, like JSO Suite would do the trick, okay? Awesome. So thank you very much for your attention, and I'm really happy to answer questions.
So we have time for a couple of questions.
Just reset the question and take it out.
When you showed that automatic differentiation package, you had special support for in-place functions. And I guess you just exploit that in the backend, then forward diff offered if you use that. Do you have some benchmarks on that? Comparing in and out of place differentiation? Because there's an open issue in abstract differentiation where they are asking for those kinds of benchmarks.
So you mean benchmarks between using in place and out of place functions? Okay, so the question was, do we have benchmarks comparing in-place and out-of-place functions in automatic differentiation? And the answer is pretty simple. I don't have benchmark, but I noticed from the very start that it's a lot slower using out-of-place functions, because I think we learn all by coding in Julia that having to allocate things is slowing down essentially the code. So. However, it's a lot more painful to do automatic differentiation with in-place functions, so it was a lot more work. And if we were to do benchmark with Zygote, for instance, usually Zygote is, on the type of figure I showed, usually Zygote is a lot slower because of these kind of things.
Thanks very much.
Thank you.
Okay, so now is my turn to talk for the next 25 minutes or so. But I noticed that no one is going to keep me honest on the time, so I'll have to get someone to yell out at me if I go over time. No, I'm not planning to go over time. So I know we still have a few more talks to come. Xavier can throw something at me if he needs to. So I guess where things left off. So last year I gave a talk on with the exact same title, Improving Nonlinear Support in Jump, and then I've come back and I'm still improving nonlinear support in Jump. And the backstory to this is that there's some folks at Los Alamos National Labs who like to solve power optimization problems, ACOPF, and they kind of complained a lot about JUMP's nonlinear support, and they said, can you improve JUMP's nonlinear support? And we said, yes. Do you have any money? And they said yes. And so that's what I've been working on for the past 2 years. They kind of asked for 3 very high-level things. The first thing was a lot about automatic differentiation and different ways of doing AD and being able to swap in and out different AD systems and compare 2 solvers with 2 ways of computing automatic differentiation. So if you want to learn more about that, go and listen to the talk last year. As part of that work, in the background, we ended up essentially ripping out all of the nonlinear stuff that was in JUMP and moving a lot of that to MathOpt interface. So at one point last year, we kind of made a new release to JUMP that, say, broke infinite opt, and Josh had to go and fix a bunch of things. So that's kind of, the AD stuff has kind of been done, but the next set of things were really about the difference in JUMP of how you can model nonlinear programs versus everything else. And they sent me one of these examples, which is something they would like to solve, where they have a model, they have some, say, symmetric matrix, and then it's got some things in the objective that are like higher order powers. Maybe they want to do some like matrix kind of subtractions between 2 things, and then sum. And anyone who's kind of written nonlinear models in JUMP can easily see that this currently doesn't work. One problem with it is that you had to know to use the @NL macro instead of the @objective macro. And so there's kind of these 2 little things in JUMP that in some cases you had to do this one thing, and in other cases you had to do this other thing, and that was a little bit annoying. But the bigger problem was that this thing does not work. If you like copy paste this in, it currently errors. Because you can't have, say, vectors inside a nonlinear expression at the moment. You definitely can't have matrices. And you can't do like the broadcasting subtractions, and you can't even do sums over vectors. So their request was, can you make that work? And this is what they're currently having to do to make this work in JUMP, is these kind of nasty little workarounds where to get x to the power of 4, you need to introduce a new temporary variable and then go x squared equals this new thing, and then that squared. And so we had kind of talked about in other talks today, where you can write down the same models in JUMP, but sometimes you have to make them a lot bigger, and being able to represent the true nonlinear form would be nicer. But it's not just Los Alamos that are having these problems. I get kind of a question on the forum, maybe not once a week, but like pretty regularly, where someone says, hey, I tried to write down this nonlinear program in JUMP, and I heard it was really cool, and then I got stuck doing things involving arrays or summations or polynomials or vector valued functions. And my answer has always been, yeah, I'll be fixing that, but it's going to take a bit of time. So the good news for this talk is that this is where we're going to tell you our plan for fixing all of these problems in JUMP. The underlying reason why we had these problems is that JUMP historically had an affine expression object, a quadratic expression object, and then all the other nonlinear stuff on the side. So you could never build nonlinear expressions as a first-class object in JUMP. You couldn't build it in the REPL, you could only build it in these weird macros, and you couldn't manipulate them or extend them or do anything like that. So what we really needed is a new nonlinear expression object in JUMP. The question is, what should this be? And this was kind of not an obvious thing when we started out. And there's kind of 2 trade-offs here that I'd like us to kind of think about. The first one is whether we should make this expression very kind of heavy or lightweight. And what do I mean by heavy? I mean we could make a big kind of expression graph where we recorded whether the expression was convex or monotonic, and we could maybe talk about polynomial components and quadratic components and exponential components, and we could add a lot of stuff into that. Or we could keep it very lightweight and just say, here is the expression graph, and this is a sine node, and that's all you get to know. That's kind of on the mathy side of things. On the actual Julia programming side of things, we need to kind of think about this typed versus untyped trade-off, where we could go kind of into the Julia type system and do lots of complicated stuff there, or we could kind of keep it as simple as possible. So what we did is we went away and looked at how other people have solved this problem in the past. One that probably a lot of people here have seen or used is this symbolics.jl package, where like jump, they have an @variable macro, and you can kind of declare variables, and then you can, I don't know, say sine of x or x squared, and it builds an expression graph. Under the hood, they chose to represent this as a set of nested structs, where we're kind of using the Julia type system to add information to our nodes in the expression graph. But it's also a bit what I would call heavy in some places, where the fields in the nodes sometimes contain, say, dictionaries and like, are these arguments sorted, and some other information that is not just what is the expression. And it's kind of sitting somewhere on this typed-untyped trade-off, where the nodes themselves are typed, but some of the arguments are just any. And so that's one choice. Maybe at the extreme end of using I won't say abusing, but using the Julia's type system is mad diff, where everything gets effectively put into the signature of the type. So if I had an int plus an int, then the type signature of expression 2 would be int plus. And then if you wanted to nest that expression, you can you keep kind of stacking these things in it, and it quickly blows out. The benefit is once the Julia compiler can kind of compile that expression, it's very fast to evaluate. The downside is it doesn't really scale beyond a few terms. But this is not a problem that is just faced by people in Julia. So how to, say, nonlinear optimization packages in other languages handle this. One option is Gravity, which is a C++ modeling tool that actually gave a talk in JumpDev 2018, which you could go and have a look up. I think it's still on YouTube. And this is in C++, but I would call it typed and heavy, because it's got a lot of stuff in here that is useful if you're, say, working with nonlinear programs, but you kind of have to carry it around. So they've split out the linear, the quadratic, the polynomial terms. They've split out whether the term is convex or monotonic. And one nice thing about Gravity is it's very fast. So at Los Alamos, they're building these big ACOBF problems, and Gravity is maybe 50% faster than Jump on some of their larger problems. I guess the trade-off is this is in C++, and some of the techniques that they use in C++ from a kind of typed, untyped choice don't necessarily translate that well to Julia. The other option in Python is Pyomo, which is a very popular modeling language similar to Jump, and they support lots of nonlinear expressions as well. And it's kind of hard maybe to do a direct comparison between, say, the Pyomo and Julia, but it's kind of similar to the symbolics thing, where they've got these specialized nodes in the expression graph with a little bit of stuff in there. So I didn't want to put the slide up and get accused of misleading benchmarks, but we went through and tested these four different things out, and they all have, I guess, pros and cons in different types of problems. Sometimes they're fast in one problem and slow in a different problem. And so we kind of stepped back and said, Julia has some unique things about its type system. We want to write down really large expressions. Is there any other example, maybe not from a mathematical modeling perspective, but is there anything else in Julia that works with large symbolic expressions of trees? And the answer is yes, just the Julia expression object. Right? So it can parse all of a Julia file, and it's actually building an expression tree of functions and stuff in it. I mean, it's not mathematical optimization, but it's effectively the same thing that we need. And the Julia expression graph has a head, which is a Julia symbol. In this case, it's a call node, but it could be a different type of node. It could be a ref or an and or something like that. And then the arguments to their functions are just a vector of any. So it has a symbol as the head and then a vector of any. And we kind of know that this works for really large problems in Julia because everybody here is using it and no one is complaining. Right? And there's maybe some work that has gone in to make this data structure of a symbol and a vector of any be efficient. So we thought, rather than trying to match what, say, other mathematical programming libraries have done, why don't we try and match what Julia has done? So in terms of this heavy, lightweight, and typed, untyped trade-off, I think we're actually choosing to go towards the lightweight end of things, because all we provide is a symbol and a vector of any, and then a kind of untyped thing, because you only have a vector of any. We're not trying to put any specialized type information into the nodes in the expression graph. So effectively, this is going to be the new design of nonlinear expression in JUMP. A head and then a vector of any, and it's just totally inspired by the Julia expression. What does this look like in practice? In JUMP, you can say, so there's a PR in JUMP. If you go and have a look, where you can kind of try and test this out. If you use that branch, it's not currently released. You can say, using JUMP, I make a model, I make a variable. Then in the REPL, you can call sine of x, and we overload all of the basic nonlinear functions in Julia for JUMP variables. And now y is a nonlinear expression. The head of this sine of x is the symbol sine, and then the args is a vector of any with just one element of x. And then inside JUMP and inside MathOpt interface, there's effectively a big lookup table of how you can convert the symbol sine into something that's useful for doing function evaluations and derivatives and stuff like that. But at the user-facing end, it's just a very simple data structure that's easy to work with. Thinking back to all of the problems that Los Alamos had with the current syntax, how do these translate to the new nonlinear expression object? One thing is that you can build up these nonlinear expressions outside of macros. So in the REPL, I can just write down x plus x to the 3 times sine of x to the x. And I can write down the same thing inside a macro, and now there's kind of no difference. So I no longer need to use the at NL expression to build nonlinear expressions. I can either build them in macros or outside of macros. I can also do vectors and matrices and things like that inside macros and outside of macros. So here's that same example of x to the 4 dot minus x to the 3 summed. In this case, I haven't shown you the big printout here because it actually ends up being a very large scalar expression with a very large number of terms, and so it kind of went down the page too much. But at least at a high level, you can kind of now write down these things as you would want to, rather than having to find all of these hacks and introduce new variables into the problem.
So you're relying on at least vector operation that they need to, you're going to let Julia scale up.
Yeah, so Miles's question for the YouTube is, how does this kind of work? And the answer is that inside Julia there are generic overloads for how you can multiply two matrices. And essentially they boil down to scalar additions and multiplications. And so we haven't written anything special for how you can multiply two matrices of JUMP variables. We just let Julia's generic dispatch kind of keep going until it finds the basic scalar plus and multiplication. So this could end up being this kind of expression swelling problem where it builds a very large expression, and then we have to go and deal with that later. And maybe in the future we could think about how to have some vector valued nonlinear function where we could explicitly write down a matrix to the 4 rather than some scalarized version. Another interesting thing that kind of plops out and is directly related to what I just said is function tracing. So now if you write down a Julia function and you don't type the input, then if you call that function with a JUMP variable, we just try and use operator overloading to try and build that nonlinear expression. So here I create a function myfunc, which is 2 to the y plus x above y to the power of minus 2.3, and it builds that expression. Previously, if you've used JUMP and you've kind of written user-defined functions, you had to register them, where then you had to kind of register it and either use automatic differentiation to compute the derivatives, or you had to manually provide those. Whereas now you can just plug in the x and it builds the expression. But there's also a way to still register user-defined functions if you know you have a complicated function and you can provide the explicit gradient. In this case, there's a new @register macro that returns you an object, and that instead of tracing the function now just stops and says, okay, here's where I'm going to stop, and I'm not going to try and evaluate it any further. So the bit in the discourse post at the start of the talk that I had kind of blocked out, and this person was saying, you know, I had this problem and I have trouble with sums and products and stuff inside nonlinear expressions. This was the model they were trying to write. In this case, it's got a nonlinear constraint. It's got a bunch of these functions, these kind of nasty things. And to write this model down in JUMP at the moment is not very nice. You can kind of do it. And in that thread, we kind of went back and forth for a while. But we had to introduce a bunch of new variables and a bunch of other things, and it was quite messy. Whereas now this just works. Because when the LHS appears as a function, and P and Q are variables, and even if P is a vector of JUMP variables, we do this function tracing thing, we build the expression, and it kind of seems to work. So I would expect a lot of models that people have tried to write down in JUMP in the past and maybe gone to a different tool because it gets a bit complicated or a bit nasty should suddenly be a lot nicer to work with. Josh also hinted about this. Because we now have a first-class nonlinear expression object inside JUMP, it's now extendable. And so he's already worked on integrating these new nonlinear expressions into infinite opt. And he already presented the benchmark, so I'm kind of repeating things here for the people in the room, but maybe for the YouTube video in the future. We built 3 different types of models in infinite opt. One of them took 7 seconds to run, one of them took 46 seconds to run, and one of them kind of just errored with a recursion depth limit. And now these things build in the new nonlinear expression branch of JUMP, and they're much faster. So I think this is a win all around. And we have some other benchmarks that show that this new first-class object compared to JUMP's previous code is about the same speed. So we kind of haven't lost anything in performance. We've gained some in some other places, and the interface is a lot nicer to work with. For people who are more interested in how this actually works under the hood, maybe if you're writing nonlinear solvers or trying to connect the JSO stuff into JUMP, there's this nonlinear expression object at the JUMP level, and there's a corresponding scalar nonlinear function at the MOI level. And they're exactly the same form. They both have the symbol as the head and then a vector of any as the arguments. And so now a solver like IPOpt is going to declare that it supports nonlinear constraints because it says, I'm going to add a constraint of this scalar nonlinear function in, for example, the interval set. And we could also, we had a talk on complementarity before. A solver like Path is going to declare that it supports the vector nonlinear function in the complementarity set. So at the MOI level, this kind of nicely integrates with all of the other stuff we've been doing. One issue that you may have been thinking along as I've been talking is this expression just has like the symbol sign and then a vector of any as the arguments. That's nice to represent it symbolically or as the expression, but how do I actually like compute with that? How do I compute derivatives or evaluate the function? And the answer is that inside the MOI.nonlinear submodule, there's a whole bunch of tools for working with these expressions and turning them into oracles that you can compute with. So the actual implementation of adding this new function support to IPOpt is like 100 lines, because all it does is it reads in the expression graph. It says, hey, MOI, can you return me oracles to compute the function and the gradient and the Hessian? And then here you go. So I guess to summarize what I've been talking about over the last 20 minutes, the pros and cons of this current design, I guess the pro is that it's simple. Right, so we chose the simplest structure that we could, which is the symbol is the head and the vector of any. It's really lightweight, so it's kind of up to you to do what you want with it. There are solvers like Alpine.jl, which needs to know about monotonicity and convexity. We've decided not to help with that. So the first thing Alpine's going to have to do is read in this expression graph and then turn it into some other format and add a bunch more information. So that's one of those trade-offs on that light versus heavy thing. Another pro is that this is already working and implemented. So we could potentially do other things, but this is the one we've kind of gone with and it's there. And in our benchmarks, it seems to perform just as well as the current version of jump. The reason being that actually jump is doing the same thing at the moment, just in a different form. So in the @nl macro, what actually happens is we're parsing the Julia expressions as the Julia expression type, where now we're passing it as this jump.nonlinear expression, which is effectively the same thing, it's just got a different name. We've also moved all of the automatic differentiation stuff out of jump into MOI, so when IPOpt says, I want to convert this expression graph into an oracle, that's all there. And then the kind of slightly weird thing about this, and Miles hinted this at the, maybe this is a jump 2.0 thing, is that our current plan for the release is that it's just a feature addition. So if you write down @nl objective or @nl constraint, everything will still work. But if you write down one of these new constraints, you kind of will get the new nonlinear expression. The downsides to this is that for a while there could be two ways of writing down nonlinear expressions in jump. If you write the @nl, you'll get the old way, and if you write the new way, you'll get the new way. And that could be confusing in the documentation or online if people are looking at old tutorials that use the old syntax and we're trying to suggest the new syntax, and there are some very subtle differences between the two. So we need to think about that transition if or when we merge the new work. So I guess our next steps for where this is going. First, we need to fix a couple of printing issues in how those expressions get printed. Maybe we can simplify some of the printing so we don't get such large expressions from time to time. We also just released a bunch of generic number support to jump for linear and quadratic functions, so we need to think about how to integrate that into the nonlinear stuff. And then this really needs some testing from people on their problems. So Josh has been doing a bunch testing it out with InfiniteOpt, but if you're solving nonlinear programs in jump, I would be very happy if you tried out this new thing and said what you liked about it and what you didn't like about it. So the best way to engage with that is to go to the jump GitHub repository. And if you just look in the PRs, there's one that it says, work in progress, new nonlinear interface. And so add that branch, try it out, and then let me know what you think. So thanks very much. So I didn't run over, I didn't steal anyone else's time, so we have a few minutes for questions.
Thank you for the nice presentation. I guess you already mentioned it when Miles asked the question during the talk. I was wondering if you can elaborate a bit more on this. Currently jump in the current version is a bit tricky to work around user-defined functions that are vector valued. And I was wondering if this new branch, like in the new way of doing things, if it has made it any easier. I know in the documentation there's like a section on how to kind of work around the interface.
Yeah, so the question was, lots of people have tried to use vector-valued user-defined functions in the current version of jump, and the answer is we can't really do that. There is a workaround where you can memorize the evaluation of the function, but it's kind of these hacks. In the new version, if you register a user-defined function, it must be a scalar, like it must return a scalar. So we haven't fixed that in that sense. But if you use the function tracing approach, and your function that you've written down actually returns some nice algebraic form, then this calling myfunc, if it returns a vector, will now return you a vector of these nonlinear expressions, and then you can use them in other places. So it solves the problem if you can trace it. It doesn't solve the problem if you need to register it. Yeah, so Miles' point was that not every function can be traced, and so yes, there will be some models that benefit from this, and there will be some that are still stuck. Anything else, or up back?
Yeah, so one issue convex is that with the operator overloading approach is when there's base functions that are products, like hcat and bcat, where it's hard to define a method to say dispatch my special implementation if one or more arguments of my type.
Yes, so the question is, with this operator overloading approach, some Julia functions like hcat or vcat that have a variable number of arguments are very hard to overload and intercept. And the answer to that is we do not. We only overload a very small subset of the Julia functions, so just the basic nonlinear primitives like the trigonometric functions, log, exponential. There are things like the inequalities. So you want to be able to write down, like in jump, if else x is greater than 0, a or comma b. You can't write this down outside of the macros at the moment because we haven't overloaded variable greater than or equal to variable. So there is still some, this is the documentation issue for releasing this, where there are still some very subtle differences in what you can do inside the macros and what you can do outside the macros. And we need to think about how to communicate that well.
When you generate this expression that you currently, let's say that I have a constraint that is like 1 to 2000 x squared, some kind of weird nonlinear function. Like you said, we have 1,000 constraints of this like a strange nonlinear function. Are you generating, let's say, 1,000 copies of the expression for the variable when you calculate it, or can you store? Are you storing, let's say, like a for loop that says like this is like 1,000 times this constraint?
So the question is, if I wrote down in jump, I wanted to write down a vector of nonlinear constraints, or like a for loop of nonlinear constraints. Do I, and it's for I equals 1 to 1,000, I'm going to write x to the I less than or equal to 1. Do I make one symbolic representation of that constraint and then plug in the data? Or do we just make 1,000 expression graphs? And the answer is we just make 1,000 expression graphs. If you go and look at my talk from last year, we talked about a new way of doing automatic differentiation, where you can then parse the expression graph and realize that there's actually a bunch of repeated structure, and then you can handle it there. So on the solver side, we can deal with that cleverly. But on the user side, we're just going to do the dumb thing and make 1,000 copies. Okay, we have perhaps one more question.
Back on the second last slide, you're pushing the AD to the solver. Didn't quite get.
Yeah, so this is more, I guess, where the code lived in jump or MRI, as opposed to when it got needed to be computed. So the solvers always needed an oracle for evaluating the function or the gradient. Previously, Jump's automatic differentiation engine was inside jump.jl. So jump, when you wrote down a jump model, it computed the gradient first and then passed that to the solver. We're computing the expression, passing that to the solver, and then the solver computes the derivatives. It's just a small structural change in where things are rather than anything like math or solver related.
You said the math option interface, or the IPOP will be computing its own?
Yeah, do you mean the solver wrapper or the solver?
The solver wrapper.
Solver
yeah,
wrapper.
Maybe in the interest of time, we will call it there, and we can talk about this afterwards. So thanks, everyone. Up next, we have Xavier Ganderbleu, who's going to be talking about multi-objective optimization in Jump. And I might ask that you just use the, do you want a cool.
Okay, thank you. And up. Okay, completely different topic. I would like to share with you a feedback that I have obtained from my student about the use of Julia, Jump, and the new package multi-objective algorithm introduced this year. So, yeah, I came just back to when I came to Jump. I came to Julia through Jump. It was in February 2016 during the French OR conference, and during a chat I was talking with our colleagues. I was looking for refreshing my knowledge about the open source software to start a new research project, and my objective at that time was to develop a solver for multi-objective optimization. And then it suggests to me to try Julia and Jump, and since, as you see, I have started very early to try an old version of Julia, and I've been convinced, and I have tried immediately the next year to introduce Jump in my course oriented in operation research. So this is the kind of course that I'm giving in operation research, and what I think is interesting, I have the chance to teach two different profiles of students in computer science in my university. Then I'm covering a lot of these lectures, but also a student with a profile in mathematics, and more recently, a student with a profile in business, so in a university in Austria. So then this year, as I've observed, after 6 years of maintaining a package, it's very difficult to get feedback from the user. Okay, a user come to you because something is not implemented, something is wrong, they are in face of a bug, but when you are trying to collect some feedback about what is good, what is less good, what is missing, difficult to get an answer. Then I've asked to my student, I proposed to my student to answer to a survey, and this is in my university in the last year of the bachelor level, and Julia, and more precisely Jump, is introduced in the labs of this course. And this year, you see, the objective is to introduce students to write models and to polish models in order to have something very good. Then explicit, implicit models, dense and sparse array, and etc. And at that time, they use the solvers to solve these models. And the project this year was about the TSP, and then we have asked to implement two well-known models, the Miller-Tucker-Zemlins, and compare to the Danzig-Ferguson-Johnson. And the first one is straightforward to implement, and the other one, as you know, we have to cut the subcycle. Okay? Then it was done with the Julia 1.8, and it was during this semester. So, quickly, the profile of those students are students in computer science, mainly programming in Java and in C++. Julia and OCaml has been introduced this year. And what is nice, Julia come just after Java and C++ in terms of what they are ready to continue for the next year. And just in asking to them, what kind of language do you like to use? You see, Julia arrive in the second position between Java and C++, which is very nice. So then, in the survey, the answer was an empty square. Then it was not guided answer, and then a lot of answers were the language and the structure was very simple, clear, intuitive, readable, and etc. About the negative answer, I want to say they complain on error management and also a little bit on the documentation. They say the documentation is rich, but so rich it's sometimes difficult to obtain the information that they are looking for. Okay, then what they say here, maybe to work a little bit again on the documentation and on the error management, maybe with the forthcoming version of Julia, the error management will be more easy now to follow for the student. About JUMP, the very good news, they say JUMP is very intuitive to be used. Easy to write variables, constraint, to solve the model easily. And this is very natural when they are writing the mathematical model and to transform it to the JUMP model. Okay. Again, what they say here, maybe is to extract data from the created model is not intuitive for the student. I want to say when we want to access to a model outside the function where the model is defined, of course, we have to refer to this. And they say, okay, we have to, everything is simple except that point. We have to take care about the syntax in order to access to the variable and etc. Okay, maybe they are expecting some method in order to help that. Okay. About the second course where I'm lecturing, it's in South Brittany. This is the profile of student is mathematician now, and now they come to me with already a background in Julia. Marc Sauveau, who is our colleagues, he introduced Julia in another course, and then here. We have moved from V-generic, this is a package that we have developed in the past, to multi-objective algorithm. And the objective of the student here is again to write models and to solve multi-objective models using very standard algorithms like lexicographics method, epsilon constraint method, but also with three objectives, the Kerlik and Saing algorithm. Okay. Then this is the configuration that used for this course. The profile of student completely different. They are mathematicians, and mainly they come to me with Python and with also Julia. Okay, and then what is very interesting, they are ready to continue with Python at the same level than Julia. And this is interesting because those students are older than in my other class. There are some teachers in a secondary school, and they say, for example, a student in science should be coded in Julia because there is not a lot of simple and very efficient language for computing modeling. Okay. Then the feedback here is very interesting, and from the multi-objective point of view, they say anyone can understand how to code in JUMP. MOA, multi-objective algorithm, is simple to handle. They say, okay, the package is new. It has been introduced during this semester. They say, with the example, it's easy to survive and to use the package. But to find the attribute and etc., maybe they need some more information about that. And maybe I can contribute during the next month on this aspect. Just to conclude, I would like to give an announcement. We are organizing in October in Paris.
So up next we have Robbie, who's going to be telling us about how to debug jump models using graph theory.
Okay, great. Yeah, my name's Robbie. I'm going to be talking about some tools for debugging certain kinds of jump models with some graph algorithms. I'll skip this introduction. And to narrow the scope a little bit, I'm not going to be talking about debugging all types of models that JUMP can support, or even debugging all the types of problems that can occur in the types of models that I do debug. But what I am going to talk about is debugging the constraints of nonlinear optimization problems. And I'm talking here specifically about scalar constraints of scalar variables, basically just algebraic expressions, equality, inequality constraints. And these constraints can have many different types of problems. You can write them incorrectly, they give you wrong answers. They can be incorrectly infeasible. They can be singular, which is the type of problem that I'm going to talk about here. And singularity in constraints of nonlinear optimization problems is a problem because it can violate constraint qualifications that nonlinear local solvers rely on, which at best slows down convergence and at worst leads to problems that just don't converge at all. And this work is all motivated by a situation where you kind of write out all the equations that you'd like to include in your optimization problem. You code them all up, you choose your data, you write an objective function, finalize everything, send it to a solver, and it doesn't converge, doesn't give you an answer. And when this happens, you don't necessarily have a lot of information that tells you exactly what went wrong. And this, I mean, this probably never happens to like any of you guys, but for me, this happens all the time, like, you know, almost every time I write a model. So to be a little more specific, an example of a model I've worked with is let's just say a countercurrent gas-solid flow reactor where we have a chemical reaction happening. This reactor is modeled as a one-dimensional PDE with one spatial dimension and a time dimension. I threw this together in infinite opt and put some initial conditions, some boundary conditions. This is just this system of equality constraints in some optimization problem, let's say, but I'll just be looking at the constraints here. So if you code this up, like I did, send it to our favorite solver, favorite nonlinear solver, IP-opt, and try to solve, in this case, just a square simulation problem. This is coded up exactly as I wrote it on the previous slide. You get this dreaded too few degrees of freedom error from IP-opt, and then the fallback strategy is for jump to relax all of the fixed variables and try to solve it again. And when this happens, it converges infeasible. So this is something that happens to me all the time, and it's not necessarily the most informative error in the world. IP-opt's not telling us exactly what we need to do to go and fix our model. So when I was a grad student and this was happening to me all the time, I kind of solicited some advice from other grad students, from my advisor, et cetera. And kind of these are some of the best practices that I came up with at the time, which were to, probably the most helpful thing I was told was to try a simpler version of the model. That can really help. Other than that, I was left to look through all of the constraints and expressions that I had written and try and figure out which one had the bug in it. And if you think about this is kind of a quadratic algorithm. So every time you make a mistake when writing your model, you have to go back through all of the constraints that you've written already and figure out which one has the typo or the faulty assumption or whatever. Right, reconsider all of your assumptions, comment out half your variables and constraints, see if that helps you narrow down where the problem is. But for the types of errors that I'm talking about here, so singularities and degree of freedom issues, there's actually a systematic approach that you can take, which is to compute a maximum matching of your variables and constraints, and that can tell you where a structural singularity is or why you have a different number of degrees of freedom than you expect. And so this is a maximum matching on the bipartite graph of variables and constraints. So we have one set of nodes for variables, one set of nodes for constraints, and we can perform a matching. The maximum matching tells us if the maximum matching doesn't include every variable or constraint, then the system is, the Jacobian of the system is guaranteed to be ranked efficient. And the type of rank deficiency that really causes problems for optimization solvers is when you have a row rank deficiency in the constraint Jacobian. And so this is helpful for identifying when there's a problem, but it's not always the most useful thing for diagnosing the source of the problem, because the result of a maximum matching is not unique. In this little two equation, 3 variable system that I wrote, we could match X or Z to the first equation. Maximum matching, not unique. So the decomposition that actually is unique and provides us with concrete information that we can use to diagnose the source of a modeling error is the Domage-Mendelssohn decomposition, which tells us, it splits our system into 3 subsets, which give us all the possible variables and constraints that could be unmatched in any maximum matching. And so these are the system of variables and constraints that are under-constrained, well-constrained, and over-constrained. And looking at these systems, I found in experience with a couple different problems has really helped me to be able to diagnose the source of singularities and degree of freedom errors. So if I throw that reactor model that I showed you earlier at the Domage-Mendelssohn decomposition, what do we see? So what I'm showing you here is the incidence matrix on the left, and then I'm highlighting the over-constrained system in the middle. And so the fact that we have an over-constrained system means that the Jacobian is guaranteed to be singular. The over-constrained system contains these variables that I'm showing right here. I'm not going to list them out one by one, but it also contains the initial and boundary conditions, and this equation in the bottom right of the slide. So I'm not going to go through this, in excruciating detail, but what we've done here is overspecified our corner conditions in this PDE. So we have initial conditions, we have boundary conditions, and if we happen to apply both of them at the corners, we overconstrain our system and get an error that we can diagnose pretty easily once we have this information. So the solution is just to relax either the initial or boundary conditions at these corners, and then we can reapply the algorithm. We see that we no longer have an overconstrained subsystem. We can send the problem back to IPOpt and actually get a solution this time. This is kind of an algorithm that I throw at all of the nonlinear optimization problems I ever solve. Really is pretty cheap and gives really useful information. It would be really nice to have it in kind of a general package, which let's just forget about that for now. Right, if we had such a package, it might have a syntax that looks something like this. You construct an incidence graph, perform some useful algorithms on the incidence graph, and then get back some data in terms of your jump variables and constraints. Would be nice to have. Right, so what I'm going to do next with this is there's a couple other algorithms that we'd like to implement. We'd like to use some of the decompositions as maybe pre-processing steps for some solvers. Maybe we'll integrate with Plasmo, integrate with MOI for some derivatives, and that's what we're doing. Thanks, guys.
Yeah, I would like to build a package that had a bunch of tools for kind of debugging, not just nonlinear jump models, but all jump models. The last little throwaway sentence of can we integrate with Plasmo was actually a fantastic segue into today's last speaker, which is David Cole from the University of Wisconsin-Madison, who's going to be telling us about 2 packages that they developed there, Plasmo and Mad NLP. So with that, I will hand you the mic, and away we go.
Thank you, Oscar. My name is David Cole. I'm in the Chemical and Biological Engineering Department at University of Wisconsin-Madison. I work under Dr. Victor Zavala there. And I've worked with 2 other students who have developed these packages, former students, Dr. Sung-Ho Shin and Dr. Jordan Jelving, and I'll share a little more about what they've done. In our lab, we focus a lot on the power of abstraction. So frequently researchers or scientists use abstractions to represent their systems, and using different abstractions can lead to unique representations, analysis techniques, or mathematical properties. And in optimization, we've been using the abstraction of graphs to represent optimization problems. So you can see, for example, here how dynamic, stochastic, PDE, or network optimization can all be represented within this graph abstraction. And within Julia, graph-based modeling for optimization is enabled through the package Plasmo. I'm confident many of you have heard of this, so I just want to give a very brief overview of it. I don't want to go too in-depth. If you want more of an in-depth look, you can look at this paper on the bottom by Jordan. Plasmo was developed by Dr. Jordan Jalving, who's a former student in our lab, and Plasmo extends jump and places optimization problems within the nodes and edges of an object called an optograph. So nodes of the graph can contain variables, constraints, and objectives, while edges of the graph contain constraints between variables on two or more nodes. Nodes essentially function as jump models, and they allow for partitioning the optimization problem into this graph structure. The syntax of Plasmo is also very similar to jump, so for those familiar with jump, it's fairly easy to pick up Plasmo. And Plasmo is largely enabled through the Julia environment and is built on top of these packages like jump and graphs, and is really enabled by those other packages. There are a couple benefits that can be found from graph-based optimization, and I'll just highlight three here. First, graphs enable modular construction of optimization problems that often follow the problem structure. Plasmo enables hierarchical graphs such that a user can create an optograph of a piece of a problem and add those optographs to a larger overall graph, creating this hierarchical structure, and then you can place linking constraints between these different graph objects. Graphs also provide useful mathematical properties. Just as one example, you can read about exponential decay of sensitivity in these papers I note here on how disturbances propagate throughout this graph structure. And then third, graphs can enable decomposition schemes, and particularly schemes that exploit problem structure. And there's been work done by both Sung-Ho and Jordan on Schur and Schwarz decompositions, which can exploit the graph structure and allow parallelization of the solver. This last point leads to a second package I've used in my research, and this is the nonlinear solver Mad NLP, which was developed primarily by Sung-Ho Shin. Mad NLP is a nonlinear solver that operates very similarly to IPOpt with a filter line search and interior point method. It's written entirely in Julia and can solve highly nonlinear problems with up to millions of variables. And previous versions of Mad NLP also have functionality for exploiting the graph structure through this package Mad NLP graph. And this is made possible in part because of the graph structure of the optimization problem results in the structured linear system that you have to solve to get the search directions in the solver. You get this block arrowhead structure that Mad NLP can exploit for some schemes. So having introduced Plasmo and Mad NLP, I next want to just share two examples or applications that I've used for these packages. And I won't go very in-depth on the code or anything. If you want to see those, the code is publicly available or will shortly be for one of the applications. So the first application is from this paper we published last year with a two-stage stochastic gas network problem. The problem simulated a 170-kilometer gas network with 11 compressors, 13 pipelines, and 25 junctions. And the goal of this problem was to find an optimal compressor policy under different scenarios. So the compressor power were the first stage variables of this problem. And you can see here on the left a visualization of a single scenario of the gas network optimization problem represented as a graph, where in this case where the blue nodes correspond to pipeline nodes, the orange nodes to junction nodes, and the red to compressor nodes. And each node contained variables corresponding to their object. And you can also see here on the right an example of 10 different demands which we used within the stochastic problem, solving over a 24-hour time horizon. So we're trying to plan a compressor policy that can meet these demands within each scenario. This problem also contains several nonlinear constraints, and we could scale the problem by changing the number of scenarios and get up the largest problem to have 1.7 million variables in it. So you can see here the structure of this problem with multiple scenarios where we put the first stage variables on a master node in the center of the figure on the left. And so these first stage variables were linked across every scenario to ensure that the compressors at each time point of the different scenarios were the same, or that the power they were using was the same. And this structure is readily exploited through Schur decomposition, which is implemented in Mad NLP. And this is in part because the number of first stage variables is much less than the number of second stage variables. I'm not going to go into the mathematical process behind Schur decomposition, but if you want, you can review the paper, and the details are in there. So we solved this problem within Mad NLP in 4 different ways, as shown in this plot, where we took this total solver time per iteration and scaled it scaled the number of variables. So we solved using MA57 as the linear solver as both a jump model and as a Plasmo optograph. And we gave Mad NLP access to 1 thread and to 30 threads when we solved the Plasmo optograph. And then we also solved this problem with Schur decomposition in Mad NLP with access to 30 threads. And you can see from the results that Schur decomposition was the fastest. It's the yellow triangles here. But it's interesting that we can actually see some significant speed up just by giving Mad NLP access to more threads. So the reason for the speed up between the top 2 lines and the middle line is parallelizing function and derivative evaluations outside of the linear solver. So MA57 has very limited parallelization capabilities, but Mad NLP is able to construct that linear system in a parallel fashion and perform these function and derivative evaluations in parallel to give speed up. The second application I want to touch on is a newer project that I'm working on with hierarchical optimization, and this is in collaboration with Dr. Harsha Gangamanavar at Southern Methodist University in Texas. In this work by Atkin et al., cited on the bottom here, they propose a 3-layer hierarchical optimization problem of energy markets. You can see here on the left a visualization of their framework. So they solve 2 different unit commitment layers, including a day ahead and a short-term layer. These are the DAUC and STUC on the figure. And these are mixed integer layers that decide which generators operate at each time point. The 3rd layer, the hour-ahead economic dispatch, or HAED, is a linear program that makes dispatch decisions on these committed generators. So each layer was split into different subproblems, and the different subproblems can have different timescales and degrees of overlap overall. So for a single day, there's 1 day-ahead problem, 8 short-term problems, and 96 hour-ahead problems. And the solutions of the layers are passed between each other. So the day-ahead layers solution get past the short-term layer, which then gets past the hour-ahead layer, creating this hierarchical structure to it. And they solve this over a 32-day time horizon for the 118 bus system from NREL. And so we use this as an application of sorts to test Plasmo's hierarchical graphs. So you can see here this problem constructed in Plasmo. On the left is the full monolithic graph for a single day with the hierarchical layers highlighted by black, red, and blue. The middle figure shows the same graph, but where we aggregate each time point into a single node. And then this last figure shows each subproblem aggregated into a single node. So these graph-based representations in hierarchical optimization give insight into the structure, and they can provide different solution approaches, like solving each time point 1 at a time, each subproblem 1 at a time, or solving the whole monolithic graph at once. And these graph-based representations can help discover new decomposition schemes, which is what we're going to be doing next within this project. And so just with that, I want to recognize funding we got from the DOE for this project, and also want to recognize the collaborators I've gotten to work with. It's been a pleasure to learn from them and get to work with them.
Thanks very much. And with that, that's the end of the official talk part of JumpDev. So I want to give all of the speakers today and yesterday another round of applause, please. There are 2 logistical things. So tomorrow we're going to have a hackathon in this building on the 4th floor from about 9 till 2. So if you're around, drop by, say hi, maybe chat to people, and I think we're going to kind of sit down and work on a few things together. There's a bunch of open issues and PRs in Jump that we need to discuss. If you want to come in and provide feedback on the nonlinear interface or any of the open things, please do that. For speakers who received Miles's email to dinner, we can either meet you at the restaurant at 6, or we can meet you here at about 5:30, and then we'll walk together. With that, thanks everyone, And I guess I'll see most of you tomorrow, hopefully.